All right, we have begun. Welcome everyone to our August Astronomy on Tap. I am Dr. Cameron Hummels. I am a astrophysicist at Caltech, and I will be co-emceeing our event for tonight with my co-host, Dr. Kaylin Henderson, who is a research scientist at IPAC, NASA Center on Caltech's campus. We are joined by two illustrious speakers, Dr. Brittany Kamai and Dr. Alex G, who are going to be presenting and then leading some discussions on the topics of gravitational waves and the first stars in the universe. So thank you all for joining us tonight. Let's see, quick announcements. If this is your first time coming, the rough schedule for tonight will be, we'll have a 20 or so minute presentation, maybe even longer by Brittany, where she'll talk about gravitational waves. And then we'll take a Q&A period for that, followed by Alex's talk, where he'll talk about the first stars, and then have a Q&A period. And then after that, we'll deal with pub trivia. That'll be pretty interactive, actually, so you can enter your answers into a web page, and then it'll pop up in real time what people are answering, and so we'll have added descriptions of the science behind the various different answers and questions. So it's usually pretty fun. In addition, we may go out of order in terms of our schedule tonight, because if you're not in Southern California or you don't know, it's very hot here, and it's in fact so hot that the power grid is being overloaded by all the people who are running their air conditioning units and things to try and keep cool. I am not running my air conditioning unit, and it is 94 degrees in my apartment. It's really spicy over here. So,
in Death Valley?
What's that?
Is your apartment in Death Valley?
Yeah, it feels that way. But the point is that one or more of us may just go down, because the Department of Water and Power has said that they're going to do rolling blackouts over the course of today and the next couple of days. So one or many of us may just disappear. Hopefully not all of us will disappear from the live stream, but if we'll just deal with what we've got to do and roll with the punches. So hopefully that isn't the issue. We have a sister lecture series. If you're interested in these talks, they occur Friday night at 7 p.m. Pacific time. I'm not sure. I think it will be on the topic of cosmic explosions, supernovae, gamma ray bursts, but I'll put out a poster and put out a YouTube live stream link in the next week or so. So stay tuned for that. Other announcements. Well, first of all, did people see the Perseids last week? Did you guys see the Perseids last week?
Oh man, so I tried. I went up into the San Gabriel, so the mountain range that's just north of Pasadena and many of the towns going east. And I woke up at 2:19 a.m. last Thursday and got up there with some friends about 3:30, 3:40. And immediately we set up and we just see, a long, bright fireball basically at zenith overhead. And that was the last one we saw all night because No, that's not true. We saw two more. So we barely saw Perseids.
Fireball is super cool. Fireball
was really cool. Yeah. My friends are not astronomers though, and I promised high with that first one, and it did not maintain.
Realize. Yeah, I mean it was hard. Like the Perseids this year, coinciding with a pretty bright moon, it wasn't the best time, especially with forest fires and stuff, and pollution, haze, and whatnot. It wasn't the greatest. So hopefully we'll get better luck with some of the later season meteor showers, like the Leonids and Quadrantids and such. But we'll see.
Did you try to take a gander? Did you go out?
No. I mean, going up and trying to see Neowise and not doing. I mean, the San Gabriel Mountains are fine, but they're not really that dark. It's not that dark of a sight. It's certainly darker than Pasadena, but it's not like Death Valley or Joshua Tree or anything like that. So I'll wait for one that I can actually get out of town and view. But anyway, yeah. Oh, and because Astronomy on Tap is traditionally held in a bar, but of course we can't do that right now. I'm, well, maybe not encouraging. I don't want to encourage beverage drinking, but I'm drinking a beverage, a Bavix Super Pills, and I'm dripping on my computer, avoiding warranty. What
Beverage too.
excellent. Hydration is important.
It's actually a hydrating. So people these days are always talking about like electrolytes and stuff, and like waters aren't enough. So this is one of the ones that I'm trying to stay super hydrated.
Yes. Excellent. Good choice.
I'm nearing the end of a self-imposed dry spell. So because I'm such a square, I have root beer.
Oh, it's great.
Come for the astronomy, stay for the math jokes. AOT.
Oh yeah, that's bad. That's bad. Root beer is good. I like root beer.
I've got my cold, delicious water, which has been de-electrolyted, I guess, because so delicious cold water.
Excellent.
Nice.
I finished all of the beer in our apartment yesterday. So
hard couple of months, really.
It's been that week.
All right. I'm going to introduce our first speaker for this evening. Let's see. All right. So our first speaker tonight is Dr. Brittany Kamai, who is an experimental astrophysicist whose research focus is on exploring the entire universe, improving gravitational wave detectors, and creating seismic metamaterials. Dr. Kamai is a Heising-Simons postdoctoral fellow, which is a joint appointment between University of California, Santa Cruz and the California Institute of Technology. Dr. Kamai cares deeply about how we do science and infuses the Aloha spirit into her practice of science. And in response to the impact of the global pandemic and the national crisis on race, Dr. Kamai has worked to support her communities and created space to recharge in her sweet camp from home backyard campground with her 2 puppies. To learn more, we've posted her website, brittanykamai.com, and Cosmo Jellyfish is her Twitter handle. So I encourage you to check those out. We have full links to everything in the descriptions for our YouTube event below. And throughout Brittany and Alex's presentation, if you have questions, I encourage you to ask them in the YouTube comment section. You can either do it during the presentation itself or afterwards, and we'll just kind of collate them if you ask them during the question. But another note, in an early instance of the flyer that I created, I totally messed up and I put Dr. Tiffany Kamai and not Dr. Brittany Kamai. Deep apologies, not only to the audience, but especially to Dr. Kamai. So very, very many apologies. But I'm really looking forward to your presentation tonight. So I will let you take it away and we'll all disappear.
Thank you, Cameron. Yes, I probably have some cousin somewhere, who knows, named Tiffany Kamai. So I will share my screen and full screen mode. Can you see this?
Yes, looks great.
Okay, I was like, y'all went away, but I couldn't like, so anyone can see this. All right, strap in, let's go. All right, so I'm gonna be talking about riding the waves of the universe. So when we're talking about the universe, this is the picture that we have. So we are basically standing on the right corner where there's stars and galaxies, and there was some point in the early universe where everything started. And so this picture, this kind of cone that you're seeing, is what we call the observable universe, a way in which we can test things and measure what's in there. And this picture is a little bit off a little bit because there are stars and galaxies on the other side. We just don't have a way to measure them. So we have this boundary of our observable universe, and we ask all kinds of questions about what's in there, what's happening. And you'll see this grid, which is the space-time background of our entire universe. So so there's some other things that maybe you haven't seen yet, which is like the stars, the galaxies, but there's also dark matter and dark energy. So when you take a pie chart of our universe, like everything that's in it, the stuff that you and I interact with regularly only makes up 4% of the universe. This other stuff, this dark matter and dark energy, is influencing the stuff we see, but it's a totally different kind of thing. And so dark energy is actually the reason I got on this path of astrophysics, because I was like, what is that? So how do we even measure the universe? And we kind of break it down in these different ways. We can look at it, we can catch it, and then we can kind of hear it is one other way. So when we look at it, these are telescopes, and these are fancy eyeballs that are way more precise than what you and I can see. And these are across all different wavelengths. And then there's particle detectors, which are these fancy detectors that try to sense all different kinds of particles we can collect. And then gravitational wave detectors, which I'll talk about. So here's some pictures, the telescopes on mountaintops. Here's another kind of particle detector. This is the ice cube with the Eiffel Tower right there. And gravitational wave detectors, which I'll talk about today. So first off, gravitational waves are ripples in space-time. So everyone at home, grab your two fists and start shaking them around. This is your new dance, your astronaut tap, gravitational waves. So what you're doing is you have two masses and they're accelerating. And that this process is creating a ripple in space-time itself. So that those ripples are called gravitational waves. So so what's really to help understand this a little further, in our everyday life experience, we use what we call Newtonian mechanics. And so life is like soccer, is that we are the players on this field. And if we're playing the game, the field's not really interacting with us. So, and the field in this sense is like the space and time in which the players are playing on it. But this revolutionary thing of general relativity is that it's much more like water polo. And so you have players who are in the field, which is a pool, and it's moving. And the motion of the pool is interacting with the players and vice versa. So when you start hearing about like these revolutions in general relativity, it's this difference in the way that we understand the field that we're playing in. And also the interactions between mass and space-time itself. So we need a ruler that's more fancy than the ruler we can pick up at Office Depot to be able to measure some dynamic space-time. And rulers are really like boats. Like these rulers are like boats. And so we need something that can sense all these different kinds of waves that come through. Let's go. You're stuck. So I'm going to take a second because you may not know what this boat is. This boat is the Hokulea. And if you've never heard this, you should definitely Google this afterwards. So this is a very important boat, and it reawakened the voyaging society, the voyaging narrative that we have in our head, in our bloodline. Yeah, it's 7 o'clock and I woke up really early this morning, so I'm doing this. So I'm originally from Hawaii. I'm native Hawaiian, and Hawaiians are connected to all these other islands in the Pacific Ocean, Polynesia, Micronesia, and Melanesia. And if you grew up on the land, you look at the ocean and think everything's disconnected. But those who grew up in the Pacific know how connected we are. And Hokulea played a big role in reawakening our voyaging heritage. Kikianalia is another boat that you should definitely look up to. The techniques used are traditional voyaging techniques, so only using the waves and the clouds and the birds. And not only did Hokulea go from Hawaii to Tahiti to like retrace our steps, they did this amazing voyage finished 3 years ago, where they connected they sailed around the entire world and created this lay around the world. So these pictures on the bottom are Hokulea in Sydney, in South Africa, and also in New York, so next to the Statue of Liberty. So check out this picture. I wanted to highlight this boat in this picture. All right, so back to space-time. So we need a dynamic ruler because when we have these objects, so when you took your two fists and they're swirling around, what you're doing is you're creating distortions in space-time. And what you're looking at in the simulation are two black dots, which are black holes. And when they're distorting space-time, which is the ripples that you see around it, they're losing energy. They lose energy and then eventually start smashing into each other. And the little wiggles on the bottom that you see are the waveform of this particular type of merger. And so we want to go and measure it. So us on Earth, if that signal comes through, it's stretching and squeezing all of Earth. This is super duper exaggerated as it comes through. So this is why we need some sort of dynamic ruler that's going to be able to measure the signal coming through. So we have our interferometers. And so what you're seeing here is a laser interferometer That red thing is the laser. You have light that goes off to these distant mirrors. And the power in these tools is that you can convert the distance change between the mirrors into a brightening and dimming of light. So interferometers are dynamic space-time rulers, and our core measurement is the difference between the length of one of the arms compared to the other ones. And we're the cool kids down here measuring this brightening and dimming. I say that every time. So when I was a grad student, I got to build an actual interferometer. This is a different experiment called the holometer. And I'm showing this just for scale. So that's me back there. And this tank is where we hold one of the mirrors. So this is much smaller than an experiment like LIGO, where when you want to put a mirror in, that's the mirror, and it's an 80-pound baby, is that you need a crane to open up this giant vacuum system. And you can see how big this entire thing is. And inside there, we keep it as clean as possible to reduce any of the particles that are in there. So that is just to give you a sense of scale of how big these interferometers are. They're not only on a table, that they are these huge, intricate machines. So LIGO is part of a ground-based gravitational wave detector. And I say ground-based because those are detectors on Earth. Is that we have LIGO in Hanford and Livingston, so Washington State and Louisiana. And we also have partners in Japan, which is Kagra. We're building LIGO India, and Virgo is in Italy, along with Geo, which is in Geo 600 in Germany. So what makes detecting gravitational waves a challenge? So if you were to just take a 1-watt laser and you put it into an interferometer with a bunch of mirrors, and you neglected all of the noise contributions like the wind or anything, you can get to a precision level that's 10 to the minus 15 meters per root hertz. So every unit you can measure that precisely. Unit of frequency, you can measure that precisely. The trouble is that the amplitude of these space-time ripples scale as the mass. So the reason you couldn't feel all of our astro-on-tap gravitational waves is like our mass of our hands is very, very tiny. So it makes it super hard to be able to measure this thing. So if you start to get a more massive object, like a black hole that's 10 times the mass of the sun, then you start to work out the numbers of that amplitude that's being generated by those black holes is 10 to the minus 18 meters per root hertz. So it's a factor of 1,000 closer. So you're starting to get closer. So that's exciting. So you just say, why don't I go back to this interferometer? I'll make it super powerful and enhance the laser power and then be able to measure it. But it's not the whole picture. So when you saw that movie of these two black holes smashing into each other, you have big amplitude, you have long wavelength waves, you have short wavelength waves. So you need to be able to recover the frequency as well. So that means we need to think about everything. I'm talking about literally everything, from the motion of atoms to the motion of the Earth to quantum noise and to even density fluctuations in the air. This is what makes detector design difficult. So when you have these interferometers and they're going bright and dim, then you're able to measure that bright and dimming as a function of time. So you take a measurement at 1 o'clock, 2 o'clock, 3 o'clock, and you make this squiggle in this bottom corner here. And this is telling you how much this length change is happening. You do the analysis by sending it through a Fourier spectrum, which is like going through a prism. And then you can say which frequencies are contributing to the overall signal. So this is the kind of thing that we look at on the low, what you're looking at to orient you. This is the low frequency to high frequency. And this is more sensitive on the y-axis and less sensitive at the top. So these instruments have this sensitivity curve. So in some bins, they're less frequent, they're less sensitive, and others, they're way more sensitive. And this is what comes out of an interferometer. So if you have some signal come by, like so say you have a giant whale, then you have this huge signal to noise saying that amplitude of that wave is much, much higher than that sensitivity. And what has been incredible is that in 2015, this was the first ever direct detection of gravitational waves. It was a super loud signal. In fact, it almost seemed like it was a cartoon because it was like, oh my God, that's the thing that we thought it was going to be. And so what you're seeing is the blue and red are the signals that are coming from the Livingston and Louisiana detectors, which map to the story of these two black holes smashing into each other. So I told you this would be a party, so it definitely was a huge party, Nobel Prize, all the like awards, this is all over the news. Just to be able to directly measure this because it was a prediction from relativity, general relativity, and we didn't have a direct measurement. So cool. So we come back to this sensitivity curve, and we have another signal that comes by. Maybe it's not as big and massive as the whale, and it's something like a neutron star, and it has a high signal to noise, and we were able to measure something awesome. So we measured neutron stars smashing into each other. And so both black holes and neutron stars are when stars die. And so this was a super, super cool measurement because you had both the signal measured from gravitational waves with the LIGO and Virgo detectors. And then you also had a telescope through every single wavelength being able to turn up and look at this thing in the sky. So it's like, yeah, it was incredible. And it's just unbelievable that it actually worked in the way that it has. So this is a picture to give you a sense of like how many different places around the world participated. So the gravitational wave detectors are in yellow, and the telescopes are in blue. And not only do you see the ones on Earth that participated, but we also had space-based detectors that were on observing this object. So I'll walk you through this image because it's one of my favorites. What you're seeing on the y-axis is the mass of the sun multiplied by some number. So this is 2 times the mass of the sun, this is 10 times the mass of the sun. And the mass of the sun is 10 to the 30 kilograms, 2 times that if you're in kilograms, 4 times that if you're in pounds, but it's a million Earths. So it's just huge, okay? So the purple dots that you're seeing are all the evidence of black holes that died after stars were living their life that we could see if we looked up with telescopes and saw any like evidence that there could be a black hole. And then the gravitational wave detectors came online, and we started measuring all of these different black holes that are way, way, way more massive. So this has really disrupted how we understand how stars die. Like, how do we even get these things that big? Like the initial ones are also way bigger than electromagnetic ones we could see. And then they merge into these gigantic black holes, which is super cool. Also in the stellar graveyard are these neutron stars. So initially what I spoke about. And so we're able to see ones that are about the same mass of the sun, 2 times as big. But then with gravitational wave detections, we've seen these merge into each other and create objects that kind of live in this region where we're not really sure, are you black hole, are you neutron star, not really sure what's happening there. So it's really exciting. And this picture kind of ties together the relationships between seeing things with telescopes and looking and hearing and sensing things with gravitational wave detectors. So there are still things that lurk below the sensitivity curve, and there are times when mergers happen and they run into how well we can measure things. So what our job is to figure out, how do we get to those objects? How can we be able to see what's out there? You go, hey, what's preventing that? So you come back to your interferometer and you're like, okay, we got a laser, we've got the vacuum state, we've got the laser making these fluctuations just from the light itself. We have, because we built up the power in there, then we're pushing on the mirrors, which is radiation pressure. We've got the motion of the atoms and the mirrors themselves. We've got the gas that's still in the chamber that's causing things. We've got the Earth shaking the mirrors. So these are the things that are affecting our sensitivity, and we have to figure out how to get rid of them. So the thing is, each of those noise sources are in different parts of the landscape. So the low frequency noise, the seismic noise, the gradient and motion of the air is in this low frequency end. Things like the motion of the atoms kind of is along this way, and quantum noise. So this is what the actual curves and the design sensitivity looks like. Here's that gray curve, along with all these different types of noises that are contributing to making this curve. And so what we do is we split off into different teams and we say, okay, what can we do to figure out how to make this even better to go away? So I work on this low frequency end. So I think about the Earth and how the shaking from seismic waves affects the detectors. And so when you have a seismic wave come through, they either shake the mirrors or they actually change the gravitational field around the mirrors. And what that means is everything that has a mass is contributing to pulling on the mirror just a tiny little bit. And so that is the gravitational gradient noise that happens when you have a seismic wave that comes through. And to be more clear, dirt weighs more than air, so we can sense that difference. So if you want to reduce the shaking, like the seismic noise engineering team has come up with this elaborate plan to suspend the bottom mirror and then have all these other counteracting masses and sensors to be able to measure that and reduce all of that. So what that ends up being is that whatever's happening on the Earth, we can reduce that shaking by 10 orders of magnitude, so 10 billion times the effect, to even be able to get to these measurements. Now, this changing gravitational field, you could put a bunch of sensors around and act as like a noise canceling headphone. And that's the progressions that we're working on to try to cancel all that stuff out. So here's one idea about potentially improving future gravitational wave detectors is, could we create an invisibility cloak around the instrument? And so this work of creating a cloak known as seismic cloaking is work that's happening in the seismic engineering field, where you would have an incoming seismic wave interact with something and be able to direct the seismic waves around some precious infrastructure. And so this is a goal for some of the seismic engineers to protect buildings and hospitals and nuclear reactors from earthquakes. And so this is the kind of work that's happening these days. And so this is the recipe for getting to cloaking, is that you have these incoming waves, it interacts with some stuff, and then you end up cloaking. And that stuff is metamaterials. And this cool new thing are these people design materials. And so you can have any kind of wave, electromagnetic, acoustic, seismic, water, and then you would design a metamaterial around that to produce some phenomenon such as cloaking or filtering or wave conversion. It's really, there's so much possibility in this. So to help put this together is that most material that we interact with are nature made. So like when neutrons start smashed into each other, meaning that like the atomic orbitals are kind of binding where you can have any features out of material. And metamaterials, you create these unit cells and put them into bulk properties to have this metamaterial itself. So I have been thinking these days about seismic metamaterials. So when these seismic waves interact with that, to create seismic cloaking or any sort of filtering and that type of thing. So in this recipe, I'm kind of in this like Moana stage where I was like, oh yes, this is gonna be great. And now I'm in like the super determined phase to like figure out how these things work. Could we make this happen? All of this type of thing. And you know, who knows how far we'll go. So the reason you think about it today is that it takes a very long time to go from your idea phase into implementing it into these gigantic interferometers. And so that time scale is roughly 15 years. So if I were to get this seismic metamaterial idea into what we would do for future detectors, then that needs to happen. The R&D needs to happen today. So to give you a sense of where we are in this generation is that initial LIGO was like putting the first car together. Is that you had to hang together these really intricate kinds of technologies and prove you could do it. Where we are today is an advanced LIGO. We're going to have another upgrade to that. So that's like the Mazda 3. In the nearer future, we'll have something like LIGO Voyager, where you'll go in there, change out the guts of the car. So kind of like the difference between like an electric and a gas engine. And in the future, we have things in Europe, the Einstein telescope, and then Cosmic Explorer in the US, where we're going to take all the bells and whistles and make that flying car of a gravitational wave detector. So if you start to ask the question, what does that do for us looking out into the universe, is that where we are today, so we are this little person right here, and we're looking back into the universe where the Big Bang happened, and this is further and further back in time. So that's like half the age of the universe. And so if you're looking for black holes that are the mass that are because of stars dying, then these are the different populations that you'll be able to measure. So when we go to the next near-term upgrade to LIGO, we'll be able to really get into these populations of these black hole systems. And then similarly with neutron stars, there's these whole populations that live out there. We're working towards getting that. And what you'll see with Cosmic Explorer is that you can start to get all of them, literally all of these black holes and neutron stars. So what that looks like in sensitivity landscape is that what we do is that we turn it on for a little while, see if it's going, measure gravitational waves, turn it off, work towards design sensitivity. LIGO A+ will be like the next generation with some new bells and whistles, like squeezed light and that kind of fun stuff. And then Cosmic Explorer is going to be this significant improvement that will be 10 times bigger with all of the super fancy technology ideas. And with that combination, then we're going to be able to measure all of these things in the universe. So in reference to Alex, like ever, the black holes and neutron stars ever created in the universe. So I talked about one part of this story of gravitational wave detectors, things that are located on the ground. So this is roughly the size of like 10 soccer fields if you put them next to each other. There's going to be space-based detectors like LISA, where the length scale between each of the mirrors, in their case it's floating gold cubes, will be 10 Jupiters. So the entire radius of Jupiter is stuck it side by side. There's other things like pulsar timing arrays that are like the size of a galaxy, so using pulsars as your detector. And then we have things, the whole scale of the universe, cosmic microwave background. And this like fits on this like landscape of shorter wavelength to longer wavelength. And so I mostly worked on the ground-based end of it. As a grad student, I was working on the Holometer, which is much tinier than LIGO. And then my first postdoc was working on LIGO and thinking about LISA. And now I'm doing metamaterials and thinking about this next generation. So this is my smattering of all things together, is that we have what we're looking at, what we're feeling, what we're hearing, this entire universe, and our detectors themselves. So hopefully we'll be able to measure the entire universe, and I'll leave it at that.
Hooray, that was awesome. Very good presentation, thank you.
Totally forgot to fix that last slide.
Oh no, that was great. That was great.
I was like, here's all the things.
And there were lots of good questions from our audience.
Okay, let me see. Or you just tell me and I'll go for it.
Okay, yeah. Let's see. The first one. Oh, I guess the first one is you alluded to there at the end. What are the off-planet experiments to complement the LIGO experiment?
Off-planet, so not Earth-based.
Yeah,
yes.
The space-based stuff.
Yeah, so there's LISA. Let me back to screen share. I really was like trying to hide my last slide, but I totally forgot to make it. My bad. Just gonna be transparent. So LIGO, Virgo, Kagra, that's all on Earth. LISA, DeSigo is the Japanese group. God, I have like, yeah, so there's a Japanese group, there's a Chinese group putting together different space-based instruments. So there's been a lot of different designs of what we could put up on above Earth. So this 10 Jupiters length scale, that's for LISA. So that's a European-led one and should be flying in 2033, 30s.
Okay, yeah. Excellent. There was a question, do we get gravitational waves when the Earth or any of the planets orbit around the sun? And if yes, what's the amplitude or how does it compare with the sort of stuff that LIGO is able to detect?
Yes. All right, so it's very tiny. Like the same way I was like, all right, take your hands and like make gravitational waves. You would take the mass of the sun and the mass of the Earth, and then you would scale it by 10 to the minus 44. I could try to do this on the top of my head, but basically the thing is the frequency of the gravitational waves would be too long for being able to see it on a ground-based detector. So you would need a space-based detector to be able to see those orbits. And the interesting thing about gravitational waves is that you have to make sure your masses aren't touching each other. So you just like have to be far enough away from them. It's part of like kind of like where it goes. Oh, so, yeah.
So LISA would be able to, I mean, probably wouldn't have the sensitivity, but LISA would be in the right wavelength range to pick up something like planets orbiting around a star.
Yeah, so there's actually a fun project of you could calculate all the exoplanet signals and you would see them in LISA actually.
Whoa.
Yeah. So yeah, no, these are actually the questions. It would be in the LISA band, but the question is like how big that amplitude is the game really.
Right.
And is that set by how close those exoplanets would be, or is there a different factor that plays into it?
Like the orbital period?
Or no, I mean even the distance of the exoplanet system to
to us.
the solar system.
Like distance is a feature, how circular the orbits are. When you have elliptical orbits, you can actually help because then you can have them in different frequency bands. You'll start to see the signal and the amount, like so how many of them, and they would start being like an unresolvable background. Really depends on like what kind of models you're using. So there's a project for you, Kaylin.
Yeah, that sounds great. You know what they say, no strain, no gain.
Hey. Yes.
There was another question. Can you elaborate more on the relationship between the speed at which gravitational waves travel and the speed of light?
Yeah. So far they travel the same exact speed, and we have not found any evidence yet for the divergence. But we're looking for it, seeing if it happens. Then we'll learn all kinds of stuff. Yeah.
Let's see. Lots of very good questions here. Can gravitational waves induce earthquakes?
No. They're so tiny. They're so tiny. Wait, let me show you. Like, let's be real.
I like that metamaterial stuff. That's super cool.
See what I'm saying? I'm like, yeah, I could talk about metamaterials all day. Here, yeah. So this number 10 to the minus. So like all the way up here is like the radius of a proton. Actually, like two more big text. So yeah, so this is a good question in terms of like how big that amplitude is of these signals that are coming through. And yeah, I showed a very exaggerated movie of the signal coming through Earth and stretching and squeezing it, but that was to like build your intuition. In reality, these things are so small. These tiny, tiny, tiny numbers. So good questions.
Okay, so no earthquakes. Okay.
No earthquakes.
Let's see. With the future LISA mission, are there any concerns about an overabundance of data?
Yeah, no, Lisa's got like really fast, like intricate questions for depending on what kinds of populations. So I did talk about the exoplanet ones, but other things that we know of, like just white dwarfs, them as binary systems, they would end up being in the LISA band. And the work right now is to figure out how do you disentangle all of these signals that sometimes might be on top of each other. So yeah, there's a cool thing is that for some of these really heavy systems, like these 40, 80 mass black holes, is that when we have LISA flying, is that LISA will be able to see it very early in its orbit. And as it's merging, then it'll merge in the LIGO band. And then we'll have such a high precision on where to point in the sky. Then all of our telescope friends will be like, cool, now we'll look. Because right now we're just like, it's over there. And they're like,
there. Yeah.
It's a little better. It's a lot better. Yeah. But that's like,
it's just like, yeah, you ask point this way. And I say, we'll take all of the telescopes point that way and we'll get like 10% of like where it is. So looking forward.
That's really cool though. I had not thought about the synergy of LISA plus LIGO and how the signals would evolve kind of from one to the other. That is so cool.
Yes.
Wow.
Yes.
All right, I'm all in.
I have a question as well, and that is, so I know you alluded to some of the other international collaborations that are putting together Virgo and Kagra and some of these other ground-based systems. Aside from gaining benefits like in being able to triangulate where on the sky it's coming from, and I guess you also gain more sensitivity to the amplitude, to lower amplitudes as well, just having more collecting area. What are the benefits of having more and more receivers?
So it's not so much the collecting area like telescopes. For telescopes, you're like, I want giant eyeballs and collect it all. So the reason we say like gravitational wave detectors are like ears is that like you have an ear and you hear something, you're like, it's over there. So if you only had one thing that zipped through, then you're like, that's why we tell our telescope friends over there. And so then because we have another ear, we're like, well, it's definitely on that side, not so much this side. And for gravitational wave detectors, you're sensitive both that way and that way. So my ears are sensitive on both sides. So you kind of want to offset your ears, just have ears all over your head. And then you can start to Yes, take that image home. And then you can have all of, like, that means you can start to reduce where in the sky that you can see it. So yeah, and also like Kagra does different kind of technology within their guts. And so we can learn from that. So LIGO runs at room temperature and Kagra is cryogenic. And they're really, really cold. They're like 4 or 10 Kelvin cold. So they're solving different kinds of questions to be able to get to the sensitivity levels that would be in step with where we are with ground base. And so we can learn from them, okay, when we want to go cryogenic, what's the pros and cons of that? When I talked about LIGO Voyager, it's cryogenic, but not like that cold. It's like cool. It's like cool. Like 77. Like we're still only using liquid nitrogen, not any helium, and it's like fancy. So anyway, so it's just kind of like those kinds of things. Like Virgo does a different suspension system, like slightly different design changes there. So there's like pros and cons. So those are the other like internal parts of how we all work together as a big happy family.
If you were to design like 10 ground-based detectors, would it be better to have this mix and match of these different designs, or would it be better to have 10 identical copies spread out throughout the Earth so that you're controlling systematic uncertainties or something?
Well, so if you talk to your theory friends and your observer friends, they're like, just keep them on all the time. So whatever it is, like keep it on. I think that's the goal, right? And so that and having them on different locations around the Earth. So like Virgo, LIGO, and Kagra's a little bit lower, but they're all very much in the northern plane. And so having LIGO India or something like in South Africa maybe would really start to help reduce the resolution of the sky. So yeah.
Okay. Very good question from Laura May. What do you think of the local opposition to the TMT given your connection to Hawaii? Controversial, but I mean, lay it out there and be your true self here, and don't feel like just because we're affiliated with Caltech that we have to kowtow to the man. So.
Oh, yes. I appreciate that. Like, I'm not gonna be like.
Yeah, I didn't think I had to warn you, but
I think
we're not gonna pull any punches here. So.
No, yeah. I think there's a lot of very essential questions that we need to answer as a community for physics and how we ever build any future detectors, right? Like there's things that we need to pay attention to of like, why is this happening and how are we like mismatched? How are we not communicating between different groups where on one hand it's like, oh yeah, we're doing everything great. And it's just like, what? So the thing is like, we need to really like, as a physics and astronomy community, because we build these gigantic instruments, then there needs to be a fundamentally different relationship with the local environment. And also just like being accountable to everything that gets promised, right? Like, oh yeah, we're like supporting the local community. So why is it that I'm in a handful of Native Hawaiians who have PhDs? When you have all of those telescopes and like, you know what I mean? Like, the thing is like, let's talk about why this is happening, right? And let's really be accountable to the words that were promised, all of it, right? So there's a lot to learn there. And I think that it's important for the physics and astronomy community to actually listen and actually start to understand and build relationships and like have conversations. So yeah, that's where I'll say about that. There's a lot in there. Like that's a big question.
Yeah. That can take up the entire session.
Yeah, strap in. Brittany's thoughts on that. Yeah.
We'll get a couple more questions and then go to our next speaker. Let's see. Will it ever be possible that a gravitational wave detected by LIGO is a merger of primordial black holes?
Okay, so actually my PhD thesis was using the holometer to see if we have little tiny primordial black holes nearby. So anyway, so primordial is a term used for things created in the very early universe, so like right around the Big Bang era. And so what that means is you can create tinier black holes than you would be able to if a star just died. And so the way in which you would be able to see them is that they would potentially be contributing to like a spectrum. So we have this stochastic background that we look for any sort of primordial black hole signatures. Or what I was looking for was just like if there was one just kind of cruising by, like if it made a signature, what would that look like? And so with the holometer, because it was at high frequencies at megahertz, it actually was exploring a very unique mass range for primordial black holes that you wouldn't be able to measure from different techniques. So yeah, it's a great question. So LIGO could, if there's just one person by, maybe. I don't know. Go along with this data.
Yeah. Okay. We'll take one more question. How do the properties of gravitational waves differ from electromagnetic waves? That's a pretty big, like, boom. But,
yo, these questions are fire. Appreciate all of them. So the electromagnetic spectrum, like they're similar in the sense that you have a wave and then you have longer ones and shorter ones. And the electromagnetic spectrum is that it's really interesting because you have fancy eyeballs and be able to measure in different wavelengths. So that's the way you have like optical telescopes that measure like what our eyeballs can see, but just really, really good. And then you go into different wavelengths to be able to measure them because like wavelengths are bigger than our head. Okay, so that's electromagnetic. The thing is, when you want to do better measurements, you put it in the sky. So the same way Hubble is a better measurement than, heck, I don't know, you guys should double check with me. But like, Hubble is above the atmosphere because the waves are coming through there and wiggling it around. Whereas gravitational waves just like cruise on through. They don't care about our atmosphere, whatever. But the difference is that we're not necessarily looking at the same object, like the way you would with telescopes. Like telescopes, you would look at the same thing and like look at the same object in the space as you would on Earth. But for gravitational waves, we're looking at different objects in space than we are on Earth. So I talked about black holes that die when are formed when stars die. But Lisa is looking for super massive black holes. So these are like 10 to the 8, what is that? 10 million, 100 million times the mass of our sun. Those things smashing into each other. Like there's no way you'd be able to measure that with LIGO because the wavelength's so long. And so that's the difference between like the electromagnetic spectrum from gravitational wave spectrum, is that you're just looking at really, really different objects. I mean, electromagnetic, you kind of look at different objects and temperature, but whatever. So yeah.
okay, cool. Well, thank you very much for your presentation and addressing all these wonderful questions. That was excellent.
Yes, thank you for all the questions.
Yeah, and we'll keep Brittany around for the trivia afterwards, but now our next speaker, Alex G. I'll let Kaylin introduce.
Thanks, Cameron, and thanks again, Dr. Kamai. That was a great talk. As an exoplanet scientist, I mean, I was listening definitely when you were talking about exoplanets, but besides 2 years ago, when Caltech just turned into a huge party after everything, it's been a while since I really heard about gravity waves. So that was awesome. Thanks so much. So it is my extreme pleasure to introduce our second speaker of the evening, Dr. Alex G. So Dr. G, he's a postdoc fellow at the Carnegie Observatories. This is kind of north central Pasadena. He is a near field cosmologist, meaning that he studies nearby stars and galaxies to understand the first stars and galaxies, the origin of the elements, and the history of the Milky Way. And he says, as kind of a fun fact, that his main lockdown activity has been eating Trader Joe's snacks. And if you are interested in learning more about his research, especially if you enjoy his talk, which I'm sure we all will, we also include a link to his website in the event description. I should also say that I heard through the grapevine that you maybe recently almost became YouTube famous. And I don't know if that's a story for another time. I'll leave that in your court. So
I didn't.
No.
Did you know that, Alex?
I did not know that.
Yeah, I heard it was something that you, there's some sort of online teaching forum or something like that, that you were like on the cusp of going viral or something. I don't know. The details conveyed to me were very, very minimal. But if
You
you'd
know
like
more
to
details than I do about this. So. I'm
Maybe
hoping you can tell me that story.
tonight his lecture is going to go viral because it's
Yes.
Yeah. Yeah, maybe the arrow of time is just going the other direction.
Around.
Taylor's rumors. Yes.
Well, thank you. Maybe this will be the seed that kicks it off. And for everybody kind of watching online, please keep it up with the great questions. You can enter them in the YouTube chat, and we can help Alex go viral. So thank you. Take it away.
Thanks so much, Kaylin. Great. Yeah, I want to tell all y'all about the first stars like ever, like in the universe. So I'm sure all of you know today that the universe is like full of stars. You know, some of these are old, some of them are young, some of them are big, some of them are small, some of them have star friends, some of them have planet friends. Some of them, you know, some of them like to wiggle, some of them are sort of not so happy at wiggling. You know, there's all sorts of different stars in the universe. But the question that I'm really interested in is like, when did all of this begin? Like, when did the first stars, like, when did they start and like, what were they like? So in order to sort of understand this, let's start again with a brief history of our universe. So Brittany gave a really awesome picture of this earlier. This is sort of my hacked together version of this. So the left side over here is the start of the universe at the Big Bang. And the right side over here is where we are today. And I sort of labeled what I think are sort of major milestones in the history of the universe. So obviously there's like the birth of the universe at the Big Bang. And what we'll talk about today is sort of the formation of the very first stars at the beginning of the universe, about 100 million years after the Big Bang. After those stars are born, you actually end up with a whole bunch of other things happening that are kind of interesting, I guess. So you have like galaxies form. Eventually, I guess we form, and like planet Earth forms about the same time as the sun. That's about 9 billion years after the Big Bang. And then, you know, there's more things that happen. There's more stars, more galaxies, planets, life. Of course, all of these are very interesting topics, but what we're going to focus on over here is this first billion years of the universe today. So let's zoom in onto this little patch of the universe. So on the left over here is like the afterglow of the Big Bang. It's called the cosmic background radiation. It's the whole universe radiating as a giant plasma screen. And at the right over here, we have sort of basically the rest of the universe, all those stars and galaxies that are forming. But this part in the middle is sort of what we're interested in today. And in particular, we're really interested in like what happens in right over here at the beginning. So after the Big Bang, there's a part of the universe that's known as the Dark Ages. And it's called the Dark Ages because like the universe, I don't know, kind of sucks at the time. There's not very much inside of it. There's no stars. There's no fun stuff. And so sort of like the first time in the universe that things sort of become interesting, at least to me, is the formation of the very first stars. And so you kind of see these little bubbles over here. So the idea is that gravity sort of starts pulling like material together, and then what it does is it squishes a bunch of stuff together, and eventually it actually squishes things together so hot that it actually ignites nuclear fusion in the center of this gas ball. And nuclear fusion is what makes stars. So there is a point in the universe where there's no stars in the Dark Ages, and then the first stars turn on. And so these stars are really unique in the history of the universe, and sort of the main reason behind that, at least to me, is that they form at a time in the universe when the universe's composition is like totally different than it is today. So back in the Big Bang, they basically make like two types of elements, hydrogen and helium. And then there's nothing else really at that time. And so what happens over here is at the time of the first stars, you actually get to make all of those other interesting elements. But that's sort of the unique thing about the first stars, is they form at a time in the universe when there's basically only hydrogen and helium. So they're just made out of those things. The other like kind of cool thing about the first stars is that because they're like so close to like the beginning of the universe, you can basically take a snapshot of what we think the universe is like really early on, which we actually have a measurement of, and then just stick it on a computer and then just run it to like super, super duper duper high resolution and like actually form a first star from like the beginning of the universe, which I think is super cool. So this is a simulation over here indicating basically the formation of one of these first stars. So this box over here is one astronomical unit, which is like the distance from the Earth to the sun from here to over there. And we're going to just watch this simulation go for a couple of years. And what you'll see over here is an object forms in the middle over here. So that's actually the first star, like in the universe. And it's actually like getting all of this hydrogen and helium material, all of this hydrogen and helium gas that's sort of coming in. And it's this like really interesting and complicated thing. It's actually like breaking up into lots of different pieces. You might get like a little friend star over here to go with this other star. And we're still like trying to figure out with these simulations whether these sort of things merge into each other or if they sort of stay apart. But what's sort of universally seen across all of these different simulations that do stuff like this is that these first stars are like really, really massive. Like they're like, the sun is already really massive. It's like 1 million Earths. Like these stars, like the smallest ones are like 10 times the mass of our sun. And most of the time, a lot of the time, they're like 100 times the mass of our sun and more. And so they're like super duper monster stars that are forming at the very beginning of the universe. So when you form a super duper monster star, it kind of dies in sad ways. So the first thing is they don't live for very long. They live like 10 million years, which is not that long compared to the age of the universe. And when they die, they tend to explode. So this is another simulation showing the formation of one of these stars. So the star is now, we're like zoomed super out. The star is like a tiny dot that you can't see at the center of this cross. But because the star is really bright, it's like blowing this gigantic bubble of gas around it. And as the star sort of nears the end of its life, you're going to see this cross brighten a little bit, and then it's going to explode. Yeah, explode. And that little puff of white material, I'm going to go back a little bit. So it exploded in that little puff of white material. That's the supernova basically blowing up pushing all of the material from the star out into the universe. And so these sorts of simulations appear to show that basically all of the first stars we think are massive enough to explode as supernova, or maybe they're actually so massive that they just like go like straight into a black hole. But whatever the case, they're all dead today. Yeah, so this is going back to our timeline. We've got the first stars over here, and sort of one of the really cool things that they do is they actually create the first heavy elements. So it's that little puff of white material that got blown out in the star explosion. That is actually the time in the universe when there's like the first heavy elements. So what do I mean by heavy elements? I mean basically like everything that's not hydrogen and helium that makes up the world today. So there's things like carbon, which is the thing that makes up most of our organic molecules. There's like the nitrogen and oxygen that makes up most of the air that we're breathing right now. There's like sodium, which is something that you're not supposed to consume a lot of, I hear. There's like aluminum that you use usually to wrap up. We're not in a pub right now, otherwise I'd be talking about all of the chicken wings or whatever, but aluminum you would wrap it up in. The silicon that actually is making up the computers that all of you are watching this particular broadcast on, phosphorus in our DNA, calcium in our bones, potassium in our like ion channels, iron in our blood, titanium in, I actually don't know what titanium is really used for. It's some cool metal. But the point is all of this stuff that like makes up the universe around us today, there was none of it over here. And so these first stars over here are responsible for making the very first of those heavy elements inside of the universe today. So I think this is like really cool. And I think, in some sense, this sort of gives you a bit of a cosmic connection to these very first stars. But then, I'm an observer, so I point telescopes at things and I ask, okay, so how much of like all of this stuff that I've just talked about have we actually seen? And the answer is this, which is not very much. It's like pretty dark. Basically, we've looked out back into about 1 billion years after the Big Bang, and we keep trying to push further over here. And we also have this like snapshot over here at the beginning, but we have this like big gap in the middle that we're trying to fill in where the first stars are actually forming. And so the question is like, how do we actually find these very first stars? So the first thing that you might think is like, well, if you build like a really big telescope, maybe you can see it. Maybe you can actually just see these stars, right? And so that's in some sense actually what many astronomers have been doing over the decades. So they've started basically trying to build bigger and bigger telescopes to see further and further. So they, you can see about like halfway through the age of the universe from the ground. If you launch a telescope into space, you can see like further and further. So the Hubble Space Telescope has sort of seen to about 500 million-ish years after the Big Bang. Whoever made this infographic was like super brilliant, and instead of putting a specific year over here, they just said future. So the James Webb Space Telescope, which is the perpetual future, is supposed to basically actually see all the way back into the era where the first galaxies are forming. But unfortunately, it's turned out that the James Webb Space Telescope won't actually see this very first generation of stars itself. It'll see like the galaxies that those first generations of stars seed, but not those first galaxies themselves. So Actually, just only a month ago, someone put out a paper basically saying, well, what would you have to build if you wanted to see the very first stars at the very beginning of the universe? And they basically concluded that you need like a 100-meter diameter telescope on the moon. It has to go on the moon because it has to be outside of the Earth's atmosphere. I guess if you think it's easier to build it in space, you could decide to build your 100-meter telescope in space. Yeah, so this is not realistic, both for practical reasons and for the fact that I want to know what the first stars are doing before I die. So we have to do something else in the meantime. And so what I'll tell you about now is like at least one of the ways that we actually learn about these things indirectly. Okay, so let's step back to the idea of the very first stars. The things we know is that they're really massive. And what that means is actually they live for like a very short amount of time, something like 10 million years. And at the end of their life, a lot of them are going to explode as supernova. In other words, they're going to do this big boom and like sort of create this puff of heavy elements that comes out. Those heavy elements don't just like disappear into the void. They actually go out, and then eventually they actually sort of fall back into some other star-forming system over here. And what we think actually is that every generation of stars after the first stars, you can make both these very massive large stars as well as smaller stars. And what's interesting about this is that low mass stars, these small stars, and these large high mass stars actually have very different behavior. So the small stars actually can live a really, really long time. So easily over 10 billion years, and as even longer than the age of the universe right now. But in contrast, the massive stars live a very short amount of time, like 10 million years. So like 1/1000th the lifetime of one of these small stars over here. And when they die, they explode as supernova. They throw out all of these heavier elements, all of that carbon, nitrogen, oxygen, iron out into the universe. And all of that material then gets incorporated into a subsequent generation of stars, which again makes both of these small stars and these large stars. And then you could just repeat this process again, right? So this large star over here so this small star is going to live forever, and this large star is going to die and explode. And that's going to enrich the next generation of stars. This is going to form some small stars and some large stars. This large star is going to explode and spew out some other material. Then it's going to form some small stars and some large stars. It's going to explode, spew out some more heavy elements, and so on and so forth. And what you can see is that over time, what's going to happen is that the total amount of heavy elements inside of the universe is actually going to increase. In other words, the composition of our universe actually is evolving with time. The other thing that's really cool is when you look at each of these generations of stars, they're actually made out of all of the material of all of their ancestor stars that have exploded before them, right? So if I look at this star over here, it's actually made out of heavy elements that were synthesized by this star and by this star and by this very first generation of stars. And if I look at this star over here, it's synthesized, it's putting together all of the heavy elements from all of the generations that have formed before that. And so each star actually preserves a history of all of its ancestors. You can sort of think of it as like a cosmic DNA. The other thing that's kind of cool is this also tracks sort of the history of our universe, right? So we start over here at the start of the universe having no heavy elements, and at the end of the universe, we have a lot of heavy elements. So it all kind of puts us together. And there's this, this is like my favorite fact about the first star. So we think that all of the first stars are gone today, but because of this whole, thing where stars explode and their ashes get incorporated into subsequent generations of stars, the ashes of this very first generation of stars actually continues to live on inside of you and me, like literally you and me. So I estimated like how much of each person is actually made of ashes from the very first generation of stars. And it turns out the answer is about a teaspoon. So I was like, I actually know what a teaspoon is now because I've been baking a lot more during lockdown, but before that, I didn't really know as much. So a teaspoon, if you hold up your pinky finger, it's about like half of your pinky finger is about a teaspoon. So about half of a pinky finger of you is made up of stardust from the very first generation of stars. Of course, it's not like this chunk of you is made up of the first generation. All of that material gets sort of dispersed around and mixed with all of the later generations. So we don't know which atom of us is made in the first stars. We just know on average how much of us is made by them. But what that also means is that it's kind of hard to figure out what's going on with the first stars by looking at stars that are born relatively recently. So the method that I actually use to study the first generations of stars is something called stellar archaeology. And the idea is very simple. The idea is we want to look for that star. that star right there. So this was the very first generation of stars. They all exploded and died. But this second generation of stars, you were able to make some of these long-lived small stars. And what that means is actually we should be able to find, and we do find, some of these oldest surviving stars just floating around in our Milky Way galaxy today. And so that's why we call it stellar archaeology. You basically go digging around inside of the Milky Way looking for stars, looking for these very old stars. And the question is like, okay, how do you know when you found one of these? And that's also very straightforward. So this very first generation of stars has no heavy elements, right? This second generation of stars is going to have almost no heavy elements. And what almost means is a subject of great debate, and people argue back and forth about what this means. But so far, we found 8 of these where everyone agrees, yeah, this is a star that formed directly out of the gas that was expelled by one of these exploding first generations of stars. So I thought I would show you a picture of one of these first stars. So one of the stars inside of this image is actually a relic from the beginning of the universe, from the from the very, very first stars. If we were in person, I would ask you meanly to pick out which one it is, but instead I'm just going to make it a little bit easier for you and tell you it's right in the middle. And it's not that one, or that one, but it's actually like that one over there. So we zoomed into this patch over here, it's that little star over there. So that star is a relic from cosmic dawn, from the very beginning, from the first it's a second generation star from the beginning of the universe. And honestly, though, like just looking at this picture, there's no way you could tell that that was the case. And the reason is because just looking at pictures of stars, we don't know what they're actually made out of. And so what we do instead is we actually we take these stars and we effectively like hold up a really fancy prism to them. It's called a spectroscope. And what that does is it takes the light from that star and it splits it into its different rainbow. So if you take a prism and you actually hold it up to the sun, you're going to get like a rainbow band of colors, right? And what you'll also notice is it's not perfectly bright everywhere. There's actually going to be these dark bands inside of that rainbow. And those dark bands are actually due to different elements that are in the surface of the star. So we can pick out some of these dark bands that come from hydrogen, some of them come from helium, some of them come from iron, some of them come from oxygen, and so on and so forth. And we pick out all of those dark bands. And the idea is that the darker the band, the more of that element that there is. And so what we do, this is literally what we do. Instead of holding up a prism, we go to one of these telescopes. This is my favorite telescope, the 6.5 meter, one of the 6.5 meter Magellan telescopes in Chile. And inside of this is basically like a super awesome prism that splits up light into all of these different colors. And we use that to basically look for the lack of these dark bands. Yeah, so the name of this particular star is a horrible telephone number that just tells you where in the sky it is. So it's at 0 hours and plus 3 degrees declination. And what we found inside of this particular star is that we could not find a single iron line inside of the entire star. There's actually less than 1 iron atom for every 20 billion hydrogen atoms inside of this star. So this is one of the, there's 2 stars like this where we haven't even discovered iron, and iron is like the easiest element to detect inside of these stars. Cool. So I told you just now about stellar archaeology, just giving you a flavor of like the type of work that I do. But that's actually only one of the ways that we can detect the very first generation of stars. So what stellar archaeology is really good at is sort of finding these big stars that explode and create enrich the second generation of stars with heavy elements. One of the things that we actually don't know for sure is whether, one of the things I always hope is true is that actually there might be some of these wee little stars that actually have survived, were born at the very beginning of the universe in that first generation and have managed to survive. And so we're out there looking in the Milky Way to see if there might be any of these first star relics that are just so low mass that they could survive until today. But one of the, there's a whole bunch of other ways. This is sort of what we've been doing up until now, but I'm really excited about what's coming up in the future. And the thing that's most immediately exciting to me is what Brittany just talked about with the merging black holes. Because what I said over here is these real big stars over here, they're so massive that they just kind of go, instead of exploding, they just kind of go down to a black hole at the end of their lives. And that kind of sucks because then we can't, if they don't explode and emit elements, then we can't see those inside of the next generation of stars. But we think that there are cases where there should be basically one star that goes whump and another star that goes whump. And what will happen is actually those 2 stars will kind of go together over time and then go and explode. Well, not explode, but be detected inside of things like LIGO, or possibly inside of, I think it'll be extremely likely when Cosmic Explorer sees all of the things will actually see merging black holes from the very first generation of stars. Just to talk about a couple of other things, there's these things that I think of as super splody stars, things from about like 150 to 300 times the mass of our sun. These stars do something called a pair instability supernova. So basically what ends up happening is they basically collapse, and then it's so hot inside of that star that it actually like everything disintegrates, and then like the whole star like blows apart in like what's called a pair instability supernova. So these are super splody stars. One of these explosions is worth like 10 of these explosions. And then as you go up to like even really big, massive stars, I think people start being like, is this thing like even a star anymore when it's like 1,000 or like 10,000 times the mass of our sun? And we think that these things actually over here are the seeds of what we call supermassive black holes. These like, you know, Brittany was saying these 100 billion, million, these super big black holes that are at the centers of all of the galaxies. We think that these things are actually probably seeded by the most massive first stars over here. Yeah, so I think that's where I want to conclude. So I hope I gave you a flavor of what are the first stars. They're these supermassive stars that are out there doing all sorts of cool things. And this is over here is sort of a list of how astronomers are trying to learn about them today. So thanks.
Excellent.
Hey, thank you, Alex.
Yay!
That was fantastic.
That's great.
I really like the terminology super splody. I'm definitely gonna
Yeah.
use that. If you want royalties, I'm happy to send them your way. That's great. Thank you so much. As with gravity waves, it's been a while since I've really thought about population 1, 2, and 3 stars. So this is very informational. We have a bunch of good questions from the audience. So, before I get to those, I'll say they also, our ever perspicacious Astronomy on Tap LA audience, they pointed out some things that titanium is featured in. So we had mentions hip replacements.
Yes.
Zara says titanium camping spork. The
Oh, I got that.
Great as well. And Dan says titanium screws after an ACL operation. I was going to say Wolverine skeleton, but I think that's adamantium. I think that's different.
Like, aren't there the fancy bikes, titanium?
Oh, yeah, yeah.
There are some fancy bikes that are titanium. They're less in vogue now that there's carbon fiber bicycles, but because those are more moldable. But yeah, there's some classic titanium. Here's a titanium spoon for camping.
Hey, why is it so tiny?
It's got to be as light as possible.
Yeah.
Right?
Just have a stick by then.
So how much early star stuff is in your spork, Cameron?
Ooh.
Well, let's see, the ratio of 1 teaspoon to my body versus size of this spork, and it's more, I don't know.
That's funny.
Not
I
very
have a question for you about these first stars, actually. So back in my day, I worked on the Pleiades, and I learned about how you can have big stars, you can make little ones like M dwarfs and all that. How do we not just have early stars that are really, really tiny that never exploded and are just kind of cruising around?
Yeah, so my hope is that there are, because I want to find one, because that's like the holy grail of like stellar archaeology, is to find one of these stars, like very first generation of stars that's still surviving. But we actually think that like theoretically they probably don't exist. And the reason is actually that because of the lack of heavy elements, it actually completely changes how the very first generation of stars form. So one of the things that is a little bit counterintuitive is that in order to make things hot, you got to make things cool. So when you form stars, like what you actually have to do is basically remove lots of like energy. You have to cool down all of the material before you can get it like dense enough to actually ignite nuclear fusion. And what those heavy elements that are in the universe today and in the universe ever after the very first generation of stars do is they actually they're really good at taking that energy out of the material that's collapsing down. But the very first generation of stars, because they don't have that, they actually can't do that. And so what ends up happening is instead of like, as sort of your blob of material collapses, what would normally happen is it'd split off into like lots of little pieces. But in the first stars, they just kind of go whoomp, down until you get to that very, very dense core. So the only way you could actually get one of those wee little stars is what you saw. There was that simulation where there was like the big star in the middle and it sort of was breaking up into pieces. If basically you have two of those kind of come by and one of them sort of kicked and you sort of make a little tiny star before it can eat up all of the other material around it and something comes by and like kicks it out of place, then you would actually see one of those surviving stars. But that's like a super rare occurrence, we think. And so as far as we know, there shouldn't be those stars. But I will say that that hasn't stopped people from looking for them, because just because a theorist tells you something doesn't mean you should believe it.
Oh, you gotta keep an eye on those theorists, like, for sure.
One of the first things I learned in grad school, actually.
That's interesting. Yeah. So that first movie that we watched from Thomas Greif, it didn't have fragmentation. Those were just like, they like spun off the side of as it was like collapsing down and rotating. It was like vorticity driven as opposed to fragmentation driven.
Yeah, it's a different, I would probably still call it fragmentation, but it's a different mode of fragmentation. Yeah.
Huh. Interesting.
Yeah.
Okay.
Yeah, that's cool.
All right, well, I'll stop asking questions because we have so many.
That was
That was the question. I kid you not, I was going to ask almost the same question because I was like,
Hey, okay, so here's my other question, and then we'll go to you know how so the early universe puts a footprint of where the kinds of gravitational potential wells are to start creating these things. But if that's different, because there's other different things happening in the early universe, so you still make these baby like teeny weeny first stars. I'm all about these teeny first stars. So that
yeah, so that's a really good question. And the answer is actually maybe. And the way that you would change this the most, and this is actually like super active research right now, but the way that you would change this the most is by changing what dark matter is made out of. And so the reason, so actually the reason I got into first stars to start with, before I realized that I just thought like it's cool to like learn about your ancestry, is like I was like, oh, this is like a cool way that you can like learn about dark matter. And because what happens is like in our current theory of dark matter, it's this thing called cold dark matter, and the idea over here is basically like you make like infinitely small clumps. Like the smallest clump of dark matter in some models is like the mass of the Earth. Those don't do anything, they just like are blobs of stuff. But cold dark matter can go all the way down. But for various reasons, people think that that might not be like the best answer to solve some of issues in astronomy. And so what ends up happening is they propose other theories, things like warm dark matter. You know, hot, cold, warm, yeah. So they used to propose hot dark matter and we ruled that out. And now they propose a thing called warm dark matter. So we're just kind of like in between. And then other people, one of the things that I really have thought is really interesting right now is a thing called fuzzy dark matter or axion dark matter, which is like, there's a whole, there's all sorts of fancy names for it. But basically all of those different theories of dark matter, if you start changing them around, you actually remove the places in the universe where the very first generation of stars is going to form. And what ends up happening is basically so the whole picture that I gave, you know, one of the reasons we got to look, one of the reasons we got to find some of these signatures is because if you change the universe, everything is theoretical, right now about what the first stars are like. And if you change that, then actually what people are finding is rather than sort of forming in those early dark matter clumps, you end up having the first stars form more in sheets or filaments. So if you make dark matter warmer, you actually end up with the first stars forming over there. And there is actually going to be sort of a different mode of fragmentation compared to what we saw. So the types of fragmentation that we showed in that particular simulation sort of relies on sort of sitting in the center of sort of this nice, happy dark matter halo. And what we don't know in great detail yet is what happens as you start doing this in a sheet or in a filament. And so if that is, but what we do know is it does seem to like make a bigger starburst. And when you have a bigger starburst, things are more complicated. You might be better at like kicking out stuff. So maybe you can get the little bitty stars that way.
Oh yeah, I'm in it for like the dark matter periodic table. Like that's what I'm like, that's what I think is gonna happen. Taking bets, anyone?
Well, we've got a bunch of good questions from the audience, so I'll jump in there as well. So Daryl asks, is fusion creating these heavier elements? So you talk about from the first generation to the second generation.
Yeah, absolutely. So nuclear fusion is responsible for almost all of those heavy elements. It could possibly be all. There's actually a really, what is the right word? active debate about whether or not these first generations of stars are going to make other types of elements that are not made through nuclear fusion. But almost all of those elements will be made through nuclear fusion, just in the cores of stars, the same way that our sun is doing or other stars that are today. But in there's actually a difference, which is that those stars, they're a little bit more compact, but we won't go into that. But yeah, it's nuclear fusion that's driving it.
Cool. Laura May is kind of coming from my angle, and she's asking, given the lack of heavy elements, do you think POP2, POP3 stars could have had planets?
Oh yeah, that's such a good question. So actually, I was originally going to make that a trivia question, which is, can the first stars have planets, these POP3 stars? Oh yeah, so I should say quickly for the terminology. So there's this horrible terminology in astronomy. So in astronomy, once you name a thing, you never change it. Just that's the rule. And so like back in the 1950s, I think it was Walter Baade, like found like 2 types of stars. And so he called one of them population 1 and population 2. And then he realized actually population 2 stars come before population 1 stars. And then because these population 3 stars because these first stars come before population 2 stars, people just started calling them population 3. So worst naming ever. But the question is like, can they make planets? And so for population 3 stars, for these first stars with no heavy elements in them, no, they can't make planets. Because there's nothing to make the planets out of. We think that in order to there's lots of theories about how planets form, but we think that probably you do need like some sort of like dust content seed in order to actually like make even the gas giant planets. So the population, so this very first generation of stars, there's not going to be planets around them. After that, actually, it starts to become an interesting question. So people have tried to find planets around stars with like the slowest amount of heavy elements possible. And I actually don't know the record holder right now, but I think it's about 1/10 the iron, like the heavy element content of the sun. I don't know. And so that's like, compared to these second generation stars, that's off by a factor of 1,000. So there's 1,000 times more heavy elements in those systems compared to these second generation stars we're looking for.
Yeah, that's interesting. While you're answering questions, I'm gonna see if I can find the answer on the NASA Exoplanet Archive.
Oh, right.
Might be able to have a live update. Yeah, that's a good question. Another good question, this comes from Arwen, asking, have we spotted first generation white dwarfs, neutron stars, black holes? So first generation stellar remnants.
Yeah, that's such a good question. So the answer right now is no. And the unfortunate thing is that actually when these either know or we don't know. Let's put it that way. So actually that super awesome like gravitational wave event, GW 150914, I still remember the number because it was a big party. Yeah.
And it was today, right? 3 years ago today?
No, that's a different one, although I am about to talk about that one as well because
let's go.
Yeah. But that very first one, which was like 2 super, like not super massive, they were 2 like 30-ish times the mass of our sun black holes that were merging together. That's actually like kind of the mass that we think that these very first generations of stars should have. And so that was like one of the really big theories going forward for like where those 2 black holes came from. So the problem is that we don't know for sure. There's lots of, I would say, more popular theories. My personal opinion is more likely, although people might differ. More popular theories about how you could get black holes that massive, like basically in globular clusters, you can get more massive black holes like that. And so I think that seems more likely, but it is possible that it could have been a first generation of stars black holes. Actually, I think we won't know for sure until we have something like Cosmic Explorer, where you can look at basically all of the black holes and how massive they are, like throughout, like when you find all of them. So that's like one of the things I'm super duper excited about for that. In terms of neutron stars, we have not, once you get to white dwarfs, I think and neutron stars, I think it's going to be hard to tell them. If you see one, it's going to be really hard to tell the difference because both, regardless of sort of the heavy element content of the star, they'll sort of all end up in a fairly similar end state. Like they'll be off in distribution of some parameters. Like, you know, they might be more massive on average compared to a typical one, but you wouldn't be able to like pick out this one is a first star. And there's so few of them that would be very hard to pick them out overall from like all of the other things that are happening. So our best chance of seeing them is actually indirectly. And this actually gets back to the thing that happened 3 years ago today that I probably should have talked about, because it was like life-changing for me, literally changed like the path of like my last 3 years of my life, which was 3 years ago. There was an amazing gravitational wave event that Brittany showed where 2 neutron stars crashed into each other. Yeah, and when those 2 neutron stars crashed into each other, you know, you can point telescopes at them because they like spew out stuff, right? And that stuff is actually like heavy elements that don't get made in nuclear fusion. It's made in something called the rapid neutron capture process, which basically happens when you explode atomic bombs. So you can like explode neutron stars. Yeah, it made gold, made gold, it made platinum, it made...
There was this cool moment when they're actually handing out, you know, the Nobel Prizes, which are metals that I think are at least partially gold. And they're getting gold for having, you know, in part what the actual like elemental origin of gold is. Science is so cool.
I know.
Middle levels, just
And for reference, our Caltech Astronomy public lecture from a week and a half ago was all about the explosive origin of elements. And it discusses at some level the rapid process, the R process, the S process, and the way that you can produce these things. So check it out in the other some of the other streams that we've had.
Yes.
So to go back to the metallicity question, I actually forgot exactly what the question is. So I hope what I'm about to say is relevant to the question. But the planet hosting star that has the lowest metal content, I don't know if this phone number will mean anything, BD plus 20, 2457C, but it's got an Fe on H, or a ratio of iron to hydrogen that's about 10% of what the sun is.
Oh yeah,
So does that sound about what you're expecting kind of for the record holder?
yeah, that's basically, I think did the same thing that you just did. So I, you know, they keep finding these things, and well, I say you keep finding these things, so who knows? Yeah.
Yeah, it's cool. It looks like there's a handful, maybe a dozen or two, in between kind of 30% and 10% of iron that the sun has, but not very many. Yeah, not a lot of metal core.
I have a quick question for you, Alex. The image that you showed that showed where we were to pick out kind of not the first generation, but the second generation from stars, and you pointed to that one, it was white. Was it white because it was a white dwarf? Or I would expect like low mass stars to be redder in color, like a red dwarf, because they're smaller, they're more long lived, they're not burning quite as hot, so they're a redder color. But it seemed to be like a whitish color. So
it's like,
why,
yeah, it's
why
like
is
super blue. Yeah, and that's actually because the heavy element. So I told a half truth when I said you can't tell which stars are have very little heavy element content just by looking at pictures of them. You actually can a little bit based on their color. And it's because what ends up happening is these stars are bluer than the typical star of their mass because they have very few heavy elements inside of them. So what happens when you have heavy elements is all of those elements like absorbing light, and they tend to like absorbing blue light more than they like absorbing red light. So that's what, you know, it's not the only reason. It has to also do with the temperature of the star, but if you have like a star like our sun or something, a lot of the light that was coming out from the inside is getting absorbed in the outer layers of the star and sort of getting re-radiated at redder wavelengths. But when you take all of those heavy elements away, you just let those bluer, whiter photons just escape the star. So actually, yeah, you can increase your chance of finding a good star by looking for blue ones. But then it gets complicated because then some of them turn into red giants, and so yeah. But yeah.
Interesting.
We've got a lot of good questions, but in the interest of time, maybe let's do one more. So Ina Marie asks, are those, you know, roughly 8 second-generation stars that you were mentioning, the kind of unambiguous ones that are outside the big debate, are those under intense scrutiny? Are a lot of people studying them? And if so, kind of what are some specific examples of things that we learned from that population of 8?
Yeah. Yes, so they are under intense scrutiny every single time. I didn't mention this, but like every single time one of them is sort of found as a candidate, like, 3 to 5 teams immediately tries to find as much telescope time as they can to basically point at these things. It's a bit of a stressful race. Yeah, so they're under intense scrutiny. They sort of, what that means is basically we try and measure the abundance of elements from every wavelength that we can. So we look in the ultraviolet if it's close enough. We look in the infrared. Usually there's nothing in the infrared, and we look in the optical as well. And what the main thing that we've learned from these, and it's actually a little bit unfortunate. So this is a subtle point, but the reason that we know that they are these second generation stars is because they all kind of belong to one class of stars where we don't think you can make them any other way. And so these are basically stars that have almost no iron. Like 2 of them have no detected iron, like less than 1 in 10 millionth of the sun. Yeah, but they actually have a lot of carbon inside of them. And so the carbon is like 0.1% of the sun. And since basically every supernova that we know of like makes iron, we think that it's sort of something unique about the very first generation of stars that is actually causing it to have this very particular pattern. And it's not just that. What ends up happening is you basically see a lot of the elements that are sort of synthesized in the outer layers of the stars, things like carbon and oxygen. And the deeper you go into the star, the less of the element that there is. And so what we think it is that you're seeing a type of star which basically when it explodes is like a partial explosion. It like throws out like sort of the outermost layers of its star, but not the innermost layers. And the rest of it just sort of goes into a black hole. And that's never been seen anywhere else before. And so we think this is a unique property of the very first generation of stars. If you were to add any other like supernova to this that we know of, you would immediately jump the iron content like a factor of 10 to the 4 higher, or 10 to the 4-ish higher. So yeah. So that's sort of the main thing. Is it seems like at least some of these first stars explode in this very weird way where they sort of like do a partial explosion. But the thing that's really frustrating about it is because we don't, if a star exploded entirely, it wouldn't necessarily have those super low iron contents anymore, and people wouldn't be convinced that it was a second generation star. So one of the big challenges right now is how do you figure out if it's a second generation star, but it sort of has closer in total content to something else? That's a homework question for you. I have my favorite answer.
Yeah, an exercise for the audience. Well, thank you again, Alex. We could do one more round of applause for Alex and Brittany. Fantastic pair of talks here.
Excellent talks, guys. Really good.
This is really, really good. Yeah. So now we can switch to the third half of the Astro Untapped. So I'm going to yoink the screen share here.
Yeah, so now we get to do pub trivia.
Oh.
So
Wait, are we on a team? Does that count?
Yeah.
Are we on a team?
Yeah, we're on a team.
Yeah, everyone is on their own team, but we're all on a team, and so there's a lot of teams. The team permutation is large. So for those of you who have joined us before, we've switched the format of the trivia since we started doing events online, and so you're probably familiar with this by now. But for those of you who are joining us for the first time, we use Poll Everywhere. So you've got your browser open to the YouTube live page. You can bring up another tab or another window and go to this URL here. So pollev, short for Poll Everywhere, .com/AOTLA for Astronomy Untapped LA. And you're not going to have to create an account or sign in or anything like that. I think it might, assign you, user 123 or something like that. But it's just a random. It's not collecting any information, I promise. And so this will allow us, as we go through the trivia questions, all of you at home can just answer on the browser, and we'll get live updates for the results. And if you are unable to do that, but you're still able to type into the YouTube chat, you can feel free to type answers in there. We'll kind of keep an eye on that as we go as well. So I'm gonna kick off the first question. So everyone should see on your Whole EV AOTLA page the option to answer this question. And Cameron, Brittany, and Alex, let me know if you guys see answers popping up in the chart. You do? Great. So question number 1 asks, the Perseid meteor shower is caused by the Earth passing through the dust tail of what comet? And the options are Halley, Comet Neowise, which you talked about a little bit at the beginning, Comet Swift-Tuttle, and Comet Shoemaker-Levy 9. And it looks as though Swift-Tuttle has jumped out to a command.
Really indeed, yeah.
Delete a.
Well,
So Shoemaker-Levy was the one that crashed into Jupiter. Is that right?
yeah. I remember that was one of the first astronomy events I remember kind of seeing on the news. And actually, my dad had a telescope that was big enough for us to go try to look at it. I don't remember if we actually did see it, but I think that was in the mid-90s, maybe?
Yeah, I feel like mid-90s.
Mid-90s, yeah. So correct, good job, everybody, or good job, 78% of everybody. It is Comet Swift-Tuttle. It is not Halley, and it is not Neowise. That was kind of a red herring, just because it's been in the news. So this is a cool image. This is not actually Stonehenge. This is an ancient city, the ruins of a city called Bloundus in near a town called Usak in Turkey, or a region maybe in Usak. And I'm probably not pronouncing those names correctly. But these are a couple of Perseids you can see streaking kind of from the top left. And this was on August 13th. So just a few days ago, a couple days after the peak actually. And I was looking this up. I didn't know this. Comet Swift-Tuttle, the one that whose dust tail generates the Perseids when the Earth's orbital path goes through that dust tail. Comet Swift-Tuttle has a diameter of about 16 miles, or about 26 kilometers, and this is roughly equal to the size of the object that wiped out the dinosaurs. But do not worry, we're not going to impact Swift-Tuttle. It last came through the inner solar system in 1992. I don't think it was quite as bright or as visible as Neowise was. I'm looking online, people said they needed binoculars. And the next time it'll be back in the inner solar system is 2126. So, if they're
Hopefully we'll still be running astronomy on taps at that point. We'll see.
Yeah. The digital cameras, maybe we'll just upload our eyeballs to the cloud or something.
Yeah.
All right, question 2. Oops. Oh.
What's going on? Here we go.
Let me make sure to activate. 1 second. All right, question 2. Who was the first African-American female astronaut? Again, we've got who was the first African-American female astronaut? Sally Ride, a good answer. Mae Jemison, a couple votes for Mae Jemison.
I see your face.
Ooh, Sally Ride. Dorothy. I shouldn't give it away. Dorothy could be correct. Mae Carol Jemison, Dr. Mae Jemison. A lot of people know their NASA space shuttle history. This is great, Dr. Mae Jemison. So we're seeing a lot of permutations on Dr. Mae Carol Jemison. I actually did not know. Everybody except for Sally Ride and Dorothy is correct. So the picture, I actually did not know her middle name, but this is Mae Jemison, and her story is wild. I did not know this. So in 1987, she became the first African-American female woman accepted into the NASA astronaut training corps. And then, let's see, what was it? I think in 1992 was her first space flight. I don't know if she did more than one. It was on the Endeavour. So it was the second flight of the Endeavour. And it was the 50th flight of the whole space shuttle program. And her whole life is totally badass. So she she actually got, not like us doctors, she got an MD from the Cornell University Medical School. And then she actually worked in LA County for a couple years before she left from there to go work in the Peace Corps in, I think, was it Sierra Leone, Liberia. And she came back from that. I think it was her first time that she applied to be an astronaut and got accepted, became an astronaut, and then went into space.
Nice.
So yeah, totally badass. All right, let's get question 3. Okay, question 3. During a recent lunar eclipse, astronomers used the Hubble Space Telescope to detect what molecule in our Earth's atmosphere? So during a recent lunar eclipse, astronomers used the Hubble Space Telescope to detect what molecule in Earth's atmosphere. Our options are methane, ozone, water, and carbon dioxide. Methane, ozone, water. Water meaning H2O, not like a liquid form of another molecule, just especially when people talk about planet formation, sometimes we use the term ice pretty loose and fast, and we don't always just mean solid H2O. We mean solid ammonia, methane, a lot of these heavier molecular building blocks.
Right.
Oh, like the way that I had electrolytes in my wawater, and then Alex had just straight up water.
I got electrolytes in my water too.
Yeah.
It's funny, an interesting little pattern here. So almost the majority of people are going with methane. Then we got ozone. Not a lot of people leaning in water.
I don't know. I even read the news article on this, and I don't know what molecule they were looking for. I thought they were looking for a biosignature.
So they were looking for a biosignature. Yeah, Alex and Brittany, do y'all have, what would your answer be?
I think I picked ozone. I can't remember, but this reminded me that we actually found water on the moon, which apparently that's a thing we all know. And I was like, how did I miss this? What?
Well, I've followed it pretty closely, and it's been a back and forth kind of game. Like during the Apollo area, they're like, it's dry as a bone up there, don't worry about it. And then in the last like 10 years, there have been a number of discoveries that have indicated that there's either water ice in the craters at the polar regions of the moon, or hydroxyl and water kind of like just subsurface in certain locations on the moon. But it's really been, I don't know, up and down in terms of, oh, do we have it? Do we not? Do we have it? Do we not? So don't fault yourself.
Okay, I was like, man, how did I miss this? Like I've been in this for a while. Yeah. Okay. Thanks.
Cool. So the answer, drum roll please,
Yes.
is ozone.
Ozone?
So, yeah, you're right. It is. So here's a really cool, I actually took this is a screenshot from, if you just Google at the bottom there where I say cool video, if you just Google that phrase use any search engine, maybe even Bing could find it, who knows. But if you just search that phrase and then go to YouTube, it'll be the first, that will be the first link, about a 3-minute video that explains this result. The animations are awesome, the explanations are awesome, and this is a screenshot of it. So what happens is, so on the right, we've got the sun, in the middle, we've got the Earth, on the very left, we've got the moon, and then in between the Earth and the moon, you can see the cute little Hubble Space Telescope. So sun is emitting light, EM radiation. Some of it goes through the Earth's atmosphere. And what the astronomers did, so this was a lunar eclipse in 2019, January, I think. So they've been working on the data for over a year. But so the light goes through the atmosphere, and the angle works out that they are able to use the moon as a mirror. And so it's reflected, and then you can see the light beams are just about to go into Hubble and be observed by Hubble. And so this allows astronomers to use a technique that we use to study exoplanet atmospheres, this transmission or transit spectroscopy, but actually to apply it to the Earth using sunlight. And so they were using HST, the Hubble Space Telescope, to observe in the UV, which is the ultraviolet, so wavelengths of light that are shorter than what our eyes can see. That wavelength regime in particular, you really want to go to space because various layers of the Earth's atmosphere will block ultraviolet light, and so you're more easily able to detect it from above. And ozone has transitions, molecular transitions in the UV, and so that's how people are able to see it. And part of the reason that ozone is interesting is because that's generated via photosynthesis. And so one of you was just mentioning this, but it's one of the short list of biosignatures, or molecules that we know are produced via biotic processes that astronomers are starting to look for, and really have been looking successfully for about 10 years, I think, with Spitzer and Hubble. And this is going to be one of the major ways that James Webb is going to change the game. Hopefully, when it launches on Halloween 2021, we shall see.
I like that plot that was generated that showed JWST future. It didn't list the date, it just said future. Okay.
Did they make that measurement because of exoplanets or because of climate change?
Oh, that's a good question. I don't actually know.
Okay. And also, like, is the resolution that you measure with Hubble, looking at the Earth this way, comparable? Would you see anything similar? Like, how do you go from like a measurement with like that higher resolution of the Earth's atmosphere and ozone to an exoplanet measurement where the resolution is poorer?
I don't think the spatial resolution matters as much in this case. I think it's just the spectral resolution.
Oh, I mean spectral resolution, right? Like.
Yeah, you could probably convolve, since at this point, the filters of Webb, for example, are pretty well defined. And so it could probably convolve what you have, like take what you know the Hubble filters to be, take what you know the Webb filters to be, and kind of map them back into each other. I was going to say a little bit like the game of telephone, but hopefully without any actual loss of information, and kind of transform between and see what you would see.
Oh wait, there's Emily Martin is a postdoc at UC Santa Cruz. She's building an instrument called PEAS, I think. So it's like kind of that in-between step of like the super high fine resolution, spectral resolution to what you would see on exoplanets. And then looking at like Jupiter or something. Emily, if you're watching, I'm sorry, but I don't remember what planet it was. Yeah. Cool.
Oh, that's cool. Yeah, those are good questions. I don't know. I study exoplanetary microlensing, so I'm only armchair.
Oh, microlensing world. Okay, got it.
Yeah, the dark side. I actually had already started this one, so people are chiming in. So the question is, the Hayabusa 2 spacecraft, which may receive an extended mission, is expected to complete its sample return from what asteroid by the end of 2020? So let's see, what do we have? We've got Ryugu is the big one. People are guessing Rosetta, Ceres. 612 is probably associated with one of those. Ultima, Apophis, I don't know that one. Thule.
Alex, do you have an answer for this question? I'm like, I don't even know.
This is fantastic. There were some really cool pictures of like an asteroid that came out fairly recently, but I can't remember the name of the mission. I literally had just looked this up too. In case you can't tell, I'm terrible at trivia.
Well, I think I did not know about this mission until, I don't know, roughly 6 months ago, when I looked this up for a previous Astronomy on Tap trivia question, I think. Okay, it looks like everything's roughly equal except Ryugu, and it turns out
that it's Ryugu.
Astronomy on Tap crowd, you are correct. So here, I hope what you can see, yeah, there we go. So the sun in yellow, this is kind of a top-down view of the orbits of a bunch of different objects. So it's in a frame of reference that's fixed on the sun. So that's the yellow object. Earth going around in dark blue, Ryugu, the asteroid, going around in light green, and then Polana, which is another larger asteroid, in red, and then Eulalia, if I'm pronouncing that right, another larger asteroid in light blue. So Polana and Eulalia are the two leading contenders for the parent body of Ryugu, the asteroid. And so what happened is, so the Hayabusa 2 mission, this is a JAXA mission, so that's, you can think of it as Japan NASA, launched in December 2014, and then I think in maybe December again 2015, it did a flyby of Earth to get a gravity boost, and it actually landed on Ryugu in February 2019, and it's wild. So it actually landed, I think, 4 different rovers onto the surface of Ryugu. And then it got some samples of rocks, did a bunch of science on the surface, got some samples of some rocks, and it's bringing them back. And the expected rendezvous, well, it's going to do a flyby. Hayabusa 2 is a flyby of the Earth again, and I think early December this year, 2020, and it'll drop off a piece of an asteroid. That is wild. We've never done asteroid sample return before. And I think it's something only like halfway through its expendables, primarily fuel. And
Let's go back.
So yeah, they're considering potential future sites for it to go visit, which is really cool. Something that's wild too. So it's gonna, like, it's not, Hayabusa 2 is not landing back on the Earth. It's like jettisoning a capsule. And the capsule, they've narrowed it down. I mean, it's kind of like gravity waves. They've narrowed it down so that it's going to land somewhere in the Australian outback. Somewhere that's going to be, this capsule of however many, milligrams of Ryugu.
The thing that I liked about it was the rovers, rather than having wheels as they roved around the asteroid, it was like a little pogo stick. So it like bounced around because the surface gravity was so low that it only had to give it a little boost and it'd go like, woo, and flying around on the surface. So I just thought that was like the coolest thing.
That's awesome.
That it's not going to bring something like gross onto Earth that's not already here.
The Andromeda
You
strain.
mean like
yeah.
COVID
20.
like
COVID, right? Yeah.
like COVID take 2.
Yeah. How do they check for that stuff?
I think they do full quarantining of, I mean, certainly for instance, with the Apollo missions, when they brought back the Apollo astronauts, they stuck them in quarantine for like 3 weeks to make sure that if they had any moon bugs or, moon viruses, that they weren't going to spread to the world. And they kept them, I'm trying to remember, I think in some museum, you can see the like Airstream little thing that they kept Buzz Aldrin and the whole crew in for 3 weeks, and they just had to sit there and like read books and stuff, which sounds actually pretty awesome. But,
so horrible.
so I'm sure like people have thought of this, and anytime something comes back to maybe not to the middle of the Australian outback, but whenever they get a hold of it, they're like, all right, stick it in quarantine. No people near it for a while. Like people take it pretty seriously, I think.
I'm just imagining Buzz Aldrin in a capsule, being like, God, I wish I just had like a smartphone or something.
Yeah.
Or not, probably.
Yeah.
Interesting. All right, cool. All right.
Next question. So HIP, that's HIP, HIP 13044b was a claimed detection using gravitational waves of what type of object? And we've got supermassive black hole, dark energy burst, supernova, and extragalactic planet. HIP 13044.
I like this one.
Yeah, this is a good one. This is a tough one.
The races, watching the race.
I want to know more about these dark energy bursts. That's what I want to know about.
Yeah, those things are wild.
Let's talk about that.
Oh man, okay, people, y'all are really enjoying a supermassive black hole, extragalactic planet, kind of coming in second. Supernova. No love for dark energy burst.
Yeah, so for reference, not to give away the goose, but I just made up the term dark energy burst. For
Okay, because I'm over here being like, all right, we need to talk about this.
It sounds cool. It sounds
Yeah, when I saw that, I was like, the hell is a dark energy burst? Never heard of it.
That's right.
So the answer, it is actually not supermassive black hole. It is also not dark energy burst. It is also not supernova. It
Actually, I got it right.
So here, we'll jump into the image in a second, but I'll say, so HIP 13044, it's I think a relatively metal poor, not nearly as metal poor as the stars that Alex was talking about. But it's in a remnant of a dwarf galaxy that orbits the Milky Way, and they merged, I don't know, something like hundreds of millions of years ago, maybe even longer. Kind of talking out of my field. And what happens then when a dwarf galaxy merges with a larger galaxy such as the Milky Way, the smaller galaxy kind of just gets turned into a stream of stars. It gets dynamically ripped apart, and that's where this star is, HIP 13044. It's in this stream, this remnants of this dwarf galaxy. And that putative planet was a claim detection using the radial velocity method, but it was actually later refuted. And this is true because it turns out that the authors did not appropriately calibrate their data. And once they did that, there was no evidence for a planet. So to date, there is no concrete evidence for a planet. But what brings us to this image is that, and Brittany and Alex, I'm hoping y'all will be able to fill in my gaps here. But there was a study recently that said that Light LISA, kind of the space-based successor to LIGO that we've been talking about, that it might be able to detect extragalactic planets. Is that something that kind of jives with the capabilities of LISA? I keep calling it LISA.
That's the other. Yeah, so this was something I was answering in one of the questions, is that you look, anything that has mass and is accelerating creates ripples in space-time, so it's possible. And so then you work out the amplitudes, and yeah, there are likely that these systems will come out. Yeah, no, this is funny because this was an idea I had, now I'm starting like crotchety old scientist. I'm just like, this is an idea I had back in the day. But don't get some planets make gravitational waves. So yeah, I'm not sure which group came out with it first, but they had put together the calculations of the impact of different orbits on being able to see it in LISA. And yeah, there's potential. If not LISA, the successor to LISA. So I talk about that because I'm in that age group where I'm like, that's possible to see beyond that. Where yeah, so that's like something to think about, is even like what's going to be beyond LISA. Like that's a project that's been going for a long time, and we will have it flying very soon, but it's part of space-based gravitational wave detection, right? So what's going to be beyond that? And maybe then you'll get these exoplanet gravitational.
I think of what you were saying, I think in the Q&A following your talk, something we've learned, especially since the advent of Kepler, and TESS is confirming it. Exoplanets are common. Exoplanets are really, really common. And so I kind of wonder if you'll just have this kind of unresolved sea of background of the kind of the addition of all of these signals from planets, and whether or not we'll actually be able to disentangle and do what we're used to in ground-based and space-based astronomy with EM radiation, which is we can point to an object and say that there's a planet orbiting it. And yeah, I'll be very curious. So any aspiring astronomers out there, there's a lot of work to be done.
Yeah, and I mean, there's also like, in addition to this exoplanet population, like you start to think about just binary stars, right? Like how much would they start contributing? And then each of them would have a different type of spectrum, like an underlying population spectrum. And so that's a way that you could start to say, you know, when they're overlapping, yes, it'll be hard, but then you can say this is more likely to be in the exoplanet collective, you know, the wide binary collective, something like this. So yes, definitely some projects people are working on to make simulations, like accurate looking simulations for those populations and see what they look like. Oh, and there's really cool projects going on with like seeing what Gaia can teach us about what the underlying populations are, and then how that's gonna be like, we'll be able to see that in Lisa. Katie Brovik, that's a name y'all should know too. She works on that.
Yeah, that's
Yeah.
cool. I'm really excited for Gaia Data Release 4. I think that's when they're going to release the astrometric planet detections as well.
Oh, cool. I didn't realize that.
I think to date, the only secure planet detected via astrometry is it Neptune?
Nice.
I don't think there's any exoplanets that
Moves
are.
a lot by astrometry.
That's funny. All right, we'll get to the next one here. So how much of your body is made of stardust from the first stars? So we've got none at all, a few million atoms, a teaspoon, or a tablespoon. How much of your body? So for those who joined us at the beginning, my esteemed colleague, Dr. Alexander G, actually, oh no, I guess it's a second talk. For those of us who joined in the middle, Dr. Alexander G mentioned this a little, and it looks like people were paying attention. This is good.
People were paying attention. That's good. Nice.
This is good. Yeah, the correct answer is a teaspoon. And funnily enough, the image that I had to show is actually the same image that you know, we all know and love at this point. So one of the things I was thinking about for this question while you were talking, giving your talk and kind of talking about this. So from the first stars, does this mean that very first generation of stars, and you could do this calculation for successive generations of stars? Or is that an insane thing to think, and that just, it doesn't work for this and that reason?
Yeah, it actually should work. At least the way that I did the calculation in the first place suggests that it should. So you can do it for each generation. So the way I do it is I count roughly how much should come out, how much material should be produced per generation, and then divide the amount of heavy elements inside of us by that amount. And so that's how I came up with the answer of 1 teaspoon. I guess it's true that for any generation, then it's about 1 teaspoon in between us and them.
Oh, interesting. Okay. Yeah. I didn't know if there would be, I don't know, some sort of like exponential drop off or asymptotic. Yeah. Okay. When I was looking this up too, for any chemists out there who are listening, a teaspoon of water, say, that's about a mole, 6.02 times 10 to the 23rd molecules. So you would have about a mole of these heavier elements from the first generation. All right, well, of any elements.
This is the first time I thought about this. So you know this picture that we use all the time, we know and love? Is that, and you see the accelerated expansion of the universe, like, shouldn't it be starting a little bit further back? Or like, you know, because equals 1, right?
In
So
the
like,
last like 2 billion years, it's showing considerable expansion. Is that what you mean?
yeah, well, I'm saying like that curve should be starting a little bit back, you know, because like once that starts kicking over, it's like half the age in the universe. That seems a little bit too late in this schematic here.
Yeah.
Or is this schematic different? Like this is what I'm puzzling over right this
I think
second.
it's mostly constrained by trying to make this visually appealing as well.
Yeah, right, sure. Okay, cool. Sure.
Yeah, we can contact the WMAP team graphic.
The NASA artist.
What is going on? That's fine. All right, so speaking of science, that segues to our next question, which is, what are the names of the 2 US-based LIGO detectors?
Names.
What are the names? I'll give you a hint. It's not Kaylin and Cameron. In fact, it's
Brittany and Alex, what?
Yeah. It might be Brittany and Alex. It's unclear. It's very. So Livingston, Hanford, Virgo, Louisiana, Washington,
Rick and Morty.
Rick and Morty. Yeah. Interesting. There's no clear.
Well, some of them go together. There's like a comma between Trump, Pence, what?
Oh, Trump, Pence, brain, Pinky and the brain. Okay. Washington, yeah. Tech. Cal and Tech. Bill and Ted. LIGO, I like that. It's LIGO.
Yeah.
True.
Okay. Hanford, pulling away. Ray, Kylo Ren, Ray, yeah. Longtime viewers of the program know that we are big fans of the Star Wars documentary series here. We appreciate the love. All right, I think people really came through. It was kind of muddled maybe at first.
Yes.
That's great.
Oh, wow. All right.
Well, there's a Cameron. There's no Kaylin. Nah, I'm not hurt. It's fine.
There's a friend. Yeah.
So here is a map. So it is. I actually just forgot the name. What is it? Livingston and
Hanford, Livingston.
Yeah.
That's the cities they're in.
Yeah.
So up in the top left here, so we've got the Hanford is in southeast. I think it is Washington State. It's in is that the one that's in some beautiful pine forest, or maybe that's the Louisiana one? Can't remember.
Hanford is not known for its beauty. That's where there's a bunch of nuclear waste that's been dumped in southeastern Washington near the Tri-Cities.
Oh yeah, I see the Livingston one east of Baton Rouge. That picture looks much more idyllic than.
So the Hanford one is in a bit of a desert, and then the Livingston one is in a bit of a swamp. And then what also is about that area is that they what is the word when you harvest the trees? They like logging. So they'll do logging near the instrument, and so those are some people who own that area. So yeah, it's what the detectors are sitting on have very different environments that they're in.
So do you have to shut down the detectors during logging season when they're actively causing acoustic noise on the detectors?
Yeah, it's definitely in the coordination of when things are running and stuff like this.
Huh.
So yeah.
I remember during one of the public talks in the year-long party at Caltech after the somebody was showing, I can't remember which scientist it was, but showed this really, really cool graphic of all these different sources of strain, which are trying to measure for grav waves, but that weren't, black hole mergers. And one of the ones that blew my mind, it's things like logging, if a big truck goes by. One of them was a large swarm of bees.
Yeah.
That's how sensitive the instrument was. And that specifically stuck in my mind is, I was like, we don't stand a chance. It's amazing that we measured.
Yeah, it's one of these things where I'm like, how does this even work? I felt that way with the holometer. I'm like, and LIGO, I'm just like, how does this hang together? Because I talked about the different parts of the technology, but the other really impressive part of this is the control system. And so the control system's you're driving your car and you're trying to stay in the lanes. But when you get LIGO going, it's you are just got your foot on the pedal and you're going up and down a mountain. So it's really intense on both sides. So you're just So all of these we can talk about Cosmic Explorer, where we're going to increase the power this much. But a really big question is, how are we going to get all of these things to the control loops to be able to be stable enough to be on? So your theory friends and your observer friends are give us all the things always. So
I wouldn't call them my theory friends. I would say we're acquaintances.
Oh, that's harsh, sir. Harsh.
We're about to get a lot of unfriends.
We're all friends, and everyone's trying to answer different questions. So, because some sources you want a very long baseline. So if you want to look for stochastic backgrounds, for example, other transient ones, you're like, okay, and you want them all on at the same time. So now you have to have Hanford, Livingston, Virgo, Kagra, India all on at the same time, right? And there's disturbances that'll happen, like storm systems too, that'll affect both detectors, and you'll get correlated noise from that. Gravity Spy is a really cool thing that people in this audience here will play with, is looking at all the way noise shows up in the detectors, and they have all these like funky shapes to them, and we have to be like, that's not a astrophysical thing. so yeah, yeah.
And I guess for a lot of those localized sources of kind of signal that aren't astrophysical, that's one of the big benefits of having these multiple detectors is, you know, even if there's a large swarm of bees east of Baton Rouge, there's probably not going to be large swarms of bees next to all of the detectors if they're on at the same time.
Hopefully not. Not until the bee epidemic of 2021.
Yeah, the great bee.
But there's also like things like the Earth, like the Earth has these, the magnetic field, and then there's resonances in them. And so you can get these correlated magnetic resonances showing up in detectors across the entire globe. So there's those kinds of things that we're constantly like asking questions, and it's like, all right, well, how big is that thing going to be? And then how much would it couple into the instrument to kind of figure out if that's like a whole research direction that needs to happen. Mm-hmm. So that's like the game that you play, like clouds are heavy, and they like in Cosmic Explorer, like we need to start thinking about that, because those density fluctuations make a difference. And so it's just like, okay, so then, you know, if clouds are that heavy and we need these big solutions, like what does that do for us astrophysically? Does that mean we can't get all of the black holes in the entire universe? You know, so then you're like playing this game between like the predictions of what should exist out there with the technology advances that we need to make, kind of a thing. And then all the money, right? Like you gotta fund these things. So and like,
yeah.
And the thing is, like, what you'll notice too is that Hanford and Livingston are as far apart as we can put something in the US. And when we talk about Cosmic Explorer, we want something 10 times as long. So the baseline's 20 miles, right? Where are you gonna put this thing? You know, so you gotta start thinking about these other features of like when you want to actually do this exploration, what other things are coming into our decision making.
Yeah. Yeah, that's a lot. It's exciting.
So huge.
All right, the next question. So we're gonna totally change regimes here. We're talking a lot about short wavelength light and grav waves, but here we have an auxiliary cable recently broke and damaged what major radio observatory popularized in film and news? Hubble, we've got Arecibo. Another vote for Arecibo, all right. We've got Arecibo.
It's like my grandparents are answering here with all caps.
Love it. I mean, I use all caps all the time.
I use all caps all the time.
Oh, mine's are like, my responses are GIFs and emojis these days. Like, I don't know what life was like before that. Like, oh, they're so good.
That's funny. All right, I think the ghost is up. It is indeed Arecibo. So here is a picture of the Arecibo dish prior to this auxiliary cable breaking. So big radio dish has a diameter that's a little bit over 1,000 feet, 1,007 feet. And then, yeah, there we go. So this is a that was taken about 100 feet. So kind of 10% the diameter, the width of the mirror. Big cable broke. I mean, and that is undeniable. And I think as I was reading about it, that the cause is unknown. Do you all know?
Yeah, it's not well understood why that cable, it didn't snap. It actually came out of its like catch. The cable itself is like a ball at the end, and it goes into a latching mechanism, and somehow it came released from that, and it's not, they don't understand at all why this happened. So it's really, It's problematic. And the thing is, so I've observed on Arecibo before, back when I turned to the dark side of theory. And you can, when you go there, you're allowed to like run around and you can run underneath the dish. So you can run under that. And I hope no one was down there when it collapsed on them. But it's also funny, they have these, so Arecibo is somewhat of a unique instrument. Not only is it, well, was it the largest radio dish? There's now a larger dish in Western China called FAST. That's a couple times the size of Arecibo. But Arecibo has been around for, almost 50 years. So it's enormous. It's 3 football fields in width. And people, you can go underneath it, but they have these signs because not only does Arecibo collect light from distant objects, it can also transmit light to distant objects. So the idea is that, so for instance, there was the Arecibo message that Carl Sagan was instrumental in sending a message out to potential alien intelligent observers that might exist. It was beamed towards the globular cluster M13, in the 1980s or whatever. But the idea is mostly that it gets used to beam a huge pulse at an asteroid or some other small like solar system based object, and then it reflects like radar. It reflects that beam back, and another detector detects that beam, and you can figure out the shape of the structure that you're hitting with this radar beam. But the thing is, you don't want to be near the dish when it's sending out this enormous amount of electromagnetic pulse. So there are all these signs that start flashing if you're like underneath the dish and it's sending out this huge pulse, because it's like, this is not going to be good for your health for you to be next to this huge burst of EMP. So get out of here.
Like hit a satellite or anything with these pulses?
It could, but I think they're very well in communication with the different satellite agencies that would be responsible for these, so that it doesn't strike those things.
Wait, but isn't like Starlink
Starlink's going to be everywhere. It'll probably be a problem for Starlink.
This is how you observe his camera to Starlink. It's
gonna take him down.
Yeah, we can use Arecibo to.
I didn't say this. Oh wait, it's on the internet. I didn't say this. Oh gosh, it's gonna be like a meme.
I'm not super familiar with radio astronomy, and especially some people are concerned about what this means for the future of Arecibo. So I looked up some of the major discoveries that were made at Arecibo, and the list is awesome. So I'm just going to say a couple. One is using Arecibo data. That's how we measured the rotation period of Mercury. For a long time, it was thought to be 88 days, and it's actually 59 days. I didn't even know that.
What? I didn't even know that's what.
No, me neither. I think because its orbital period, I think, is 88 days, and I thought it was a lot. But so I learned a thing. Thank you, Arecibo. Also, the existence of neutron stars was definitively confirmed using Arecibo, in addition to the first binary pulsar, which later led to
Pulse-Taylor.
And the first exoplanets. I didn't know it was actually using Arecibo. So the first exoplanets are what are referred to as pulsar planets. So pulsars are neutron stars that they're emitting light at their poles, their magnetic poles, and they're rotating really quickly, sometimes as quickly as hundreds of times per second. And if their angle is angled the right way, they look like lighthouses to us, where we see this pulse with a certain periodicity. And if you see deviations from that periodicity, something funky is going on astrophysically. And this is actually in 1992 how the first exoplanets were discovered. Alex Wolshin, who's at Penn State now, noticed deviations in the otherwise very precise period of a specific pulsar. So I had no idea that Arecibo really has been instrumental, pun intended, in a lot of different science. All right. I do. Next question, we've got, how fast is the moon drifting away from the Earth? No, it's not receding at any measurable rate. Yes, at the speed of human fingernails growing, about 2 centimeters per year. Yes, speed of a sloth moving, about 0.002 miles per hour. Or yes, speed of a human walking is about 2 miles per hour. We got fingernails growing, sloth moving, human walking, or not at all.
I like sloth because they're cool and cute.
I like those sloths.
I should not bias anyone's answer. That is only based on
Yeah, look at that sloth boat.
yes. Drifting away from the
Looks like people have identified a favorite here.
Yeah.
I love it when you put numbers into like real life things you can wrap your head around.
Yeah.
Human fingernails growing, sloths moving, humans walking.
Alex, do you have a guess or do you know?
I was gonna say I don't know what a centimeter per year is in miles per hour.
Oh, because that'll be
I wasn't sure. I was like, I think sloths move faster than that.
oh yes, the
No,
unit.
I looked it up, and that is in fact the average speed of certain species of sloth. That's pretty good sloth. I was amazed.
You know, people come here for astronomy, but you walk away with all kinds of new knowledge.
Yeah, exactly.
Okay, so the
Know this. This is amazing.
it is the speed of human fingernails growing.
Yeah.
And here's a couple images. Cameron, if you want to describe these.
Yeah, so a few of the Apollo missions dropped off these things that are on the left. They're called retroreflectors, and they continue to sit on the surface of the moon, and they're comprised of a metamaterial that is alike to the sort of stuff that's in the reflectors on like stop signs or highway signs, so that when you shine light at them, they reflect the light directly back to the source of the light. So that allows you, with a laser, like is shown on the right, or any kind of correlated light source, to send it to them, and then it'll shine back to directly or to near the source. And then you can measure, using radar, you can sense the distance by timing it. How much time is it taken for that light pulse to get to its reflectance point and then back to the origin. You can figure out the distance. And that allows us, or has allowed us for the last 50 years or so, to figure out how quickly or how far away the moon is. And thus, if you take repeated measurements, how quickly it's changing that distance. And it looks like it's, yeah, this very slow speed of a couple centimeters or almost an inch per year. But what's interesting is that over time, these reflectors have gotten less efficient. We haven't been able to get as much light back from them as we did 50 years ago when they were first put on the moon. And it's theorized that they're slowly getting covered with the dust on the surface of the moon, and that's hindering their efficiency. But it's interesting because the moon doesn't have an atmosphere. So it's not like a wind is blowing some dust on this thing. It's just potentially that there's this slow, like the Earth, the moon is constantly being bombarded by meteors, except they don't burn up in the atmosphere. They just strike the surface of the moon and cause a little micrometeorite, a little dust grain that hits, and it kicks up a little bit of the lunar dust, the lunar regolith, and potentially that's going to slowly cover any kind of surfaces that are there. And that's a really fine dust, so it could be responsible for what's going on up there. What's interesting is astronauts who, from the Apollo missions, when they walk around, they get some of that dust on their suits, and then they go, of course, they can't smell it when they're in their suits because it's all airtight and they're breathing their own air source. But then they go back into their capsule and take off their suit, and they describe the smell as like spent gunpowder. It's pretty interesting. So people are, I think there was recently a perfume maker who did the eau de lune or something like that consisted of trying to capture the smell of what it's like to be on the surface of the moon, which I think is pretty awesome. So
that's super awesome.
To help prepare like astronauts that may be going there in the future as part of the Artemis mission or the next generation moon missions, to be like ready, have everything simulated to the nth degree.
Hey, did they pick up that piece of trash before they left?
Yeah, they should pick that up. Let's
Yeah.
leave it a pristine space, guys.
But
So-
and also these like the lunar laser ranging tests general relativity from the precision in these measurements. So it does
That's
some
right.
things. Yes.
I don't know if this is a silly question, but would cosmic rays be doing anything to degrade the instrument, or since there's no electronics, since it's just reflecting?
Slowly, yes. Slowly, yes, in the way that everything gets degraded at the molecular level by constant bombardment by cosmic rays. But because these are macroscopic objects where the reflectors are reasonably like macroscopic sized, that the time scale over which they degrade due to cosmic rays, I think, is very slow.
Yeah, the flux is not gonna destroy significant reflectivity. Okay.
No, it's not like an electronic chip that could degrade, like a CCD or something, where degradation takes place on the order of years. This is more, I imagine, on the order of centuries or millennia.
Yeah. Okay. Makes sense. And for our final question, last but not least, longtime viewers of the program are familiar with our love of the Star Wars documentary. So in the documentary series Star Wars, what was the first planet destroyed by the Death Star? Our options are Alderaan, Tatooine, Mandalore, Dantooine, or Yavin.
Ooh, Yavin. Yeah.
Yavin.
All significant systems.
All significant systems, one of which is no more.
I felt a great disturbance in the Force, as if millions of voices suddenly cried out in terror and were suddenly silenced. I fear something terrible has happened.
As the great philosopher O.W. Kenobi once said. Okay, so nobody thinks it's Mandalore. Put in Mandalore because people
Yeah, everybody loves Baby Yoda.
have been watching Mandalorian.
You can't not love Baby Yoda.
Yavin, people might be the least familiar with Yavin. Yavin 4 is the moon that the rebel base from which the Battle of Yavin was launched, wherein the first Death Star was destroyed. So that is where Yavin
Spoilers.
Yeah. The statute of limitations on episode 4 has passed. I have no regrets. And there's Dantooine, Tatooine. But as most people have correctly identified, it is indeed Alderaan. So Alderaan, here's an image, not a August rendering. These are real data. You can thank the astronomers.
Straight from the Wikipedia.
It's a planet located in the core world, so that's separate from, say, the Outer Rim territories. This is actually Leia Organa's home planet, and indeed, it was destroyed by Grand Moff Tarkin. And something I learned on Wikipedia today is that Grand Moff Tarkin's first name is Wilhuff. So his name was Grand Moff Wilhuff Tarkin.
I think we need more titles like Moff and Grand Moff.
I don't even understand all those words that just came out.
What
just happened?
Brittany, I dub you a Grand Moff. Alex, you may only just be a Moff, but you're still greater than me.
Yeah, I'm a subpar Moff, I believe.
Yeah.
So I also learned, and everybody get your tinfoil hats on. So Alderaan when it existed, its day was 18 Earth hours long. Its year was 364 days, and its diameter, and this is true, was 12,500 kilometers. The diameter of the Earth is 12,700 kilometers.
Wait, what do you mean this is true? What is it from the documentary?
Well, this is from the encyclopedic database of planets in that far, far away galaxy.
Oh, I see. Okay.
So one of the other cool things I found is, so this is a picture of Alderaan before the explosion, and it actually, just to compare what it looked like after. It's pretty cool. So you can kind of blink the two and see if you see a difference after it was destroyed by the Death Star.
Nice.
So,
I don't see any background stars, Caitlin. I don't see any background stars. I think you just used a black screen.
Whoa.
Hey, like Shouldn't there be like fragments like hanging around and like
Yeah.
water
Yeah.
and like dust?
Maybe Alderon's still there. Maybe it's
Caitlin, you just
water.
got called out. I think there's a lot
I'm part of the
this.
I'm part of the there never was an empire contingent. Alderon exists.
Yeah.
So that's the end of the trivia. Thank you everybody for playing. We hope you enjoyed it. It's a completion award. Everybody wins. Everybody gets 100%. Even normal Moff Cameron Helmets.
Even no, I'm sub off.
The Barma sub Moff.
Saying M-O-F or
MOFF, 2 F's.
Okay. All right, I
Yeah,
gotta write this down.
Grand Moff Tarkin.
Yeah, while you're looking up tricky things to spell, Kashyyyk, the planet of the Wookiees, it has 3 Y's.
Yeah.
Often people think it only has 2 Y's, but it's got 3.
Good to know. I'll put that in my search after
Yeah.
this.
Gotta make sure.
Yeah.
All right, everyone. Thank you for sticking around. Thank you. Many thanks to our excellent, esteemed guests, Dr. Alex G. and Dr. Brittany Kamai. You've been great. Thank you for your presentations and answering all of the wonderful questions from our audience. Great job, Kaylin, except for your sass and your non-fictional presentation of the destruction of Alderaan.
And Star Wars. It's not just Alderaan.
So as I mentioned at the beginning, we have these events once a month. Our next one is, I think, set for the 14th of September. I haven't yet gotten speakers, but I'm sure it'll be great. So check back into our website or social media or this YouTube channel. We'll have our public lecture on September 4th, Friday night at 7 p.m. Pacific time. I'll post that soon. In addition, if you're interested in astronomy events like this, we have sister events. There's Astronomy on Tap at University of Texas, Austin, which is having an event tomorrow night, which I encourage you to check out. They're in our featured channels down below somewhere in this YouTube channel. Furthermore, there's a similar series called Science the Show that's done in Los Angeles, which is a combination between a comedian and a scientist. The next one is about exobiology with a NASA JPL scientist speaking. I don't know who the comedian is, but I'm sure it's great. And I retweeted that on Twitter today, so you can check out and find the information. But thanks for sticking around. Thanks for chiming in, having great questions, and we'll be back next month. So have a great month. Stay diligent, wear your masks, and we'll beat this damned COVID. So have a great night, everyone.
Yes. Bye.
Night, everyone.
Okay. I ended the stream.
Okay.